Greetings, ladies and gentlemen. With great delight, you are welcome to the 4th International Virtual Conference of the Faculty of Pharmacy, University of Lagos, Nigeria. I am Dr. Florence Ukemekule, standing here as the moderator. The conference promises to be a very insightful and impactful event. We will start with an opening prayer. We therefore ask the Almighty God to make this conference a huge success. Amen. It's now time to take the national anthem, followed by the University of Lagos anthem.
Nigeria, we hail thee. Nigeria, we hail thee. Our own dear native land, though tribe and tongue may differ, in brotherhood we stand. Nigerians old and proud to serve our sovereign motherland.
Again, I welcome you all to the Future Ready University, the University of Lagos, and the nation's pride. It's now time to recognize the important dignitaries in our midst. We start with the host, the chief host of the university, the Vice Chancellor, Professor Folashade Tolulope Ogunsola, OON, FAS. The Deputy Vice Chancellor, Academic and Research, Professor Bolanle Obo. The Deputy Vice Chancellor, Management Services, Professor Olumuyiwa Falaye. The Deputy Vice Chancellor, Development Services, Professor Afolabi Leshi. Want to recognize the University Librarian, Mrs. Abosede Weekly. The University Registrar, pardon me, Mrs. Abosede Weekly. The University Bossa, Mrs. Olua Tumilola Adekunle. We want to recognize the University Librarian, Professor Olatokunbo Okiki. We want to recognize the Dean, Faculty of Pharmacy, Professor Sunday Adeshegun. And we want to recognize all the important dignitaries seated here virtually and those that are on site. It's now time for the opening remark. It's now time for the opening remark by the chairperson of the planning committee in the person of Professor Margaret Shofidia. Thank you, Prof.
Thank you very much, Dr. Nkemewule. Distinguished audience, thank you very much. I warmly welcome you to this year's conference. The Vice Chancellor, Professor Folashade Ogunshola, ONFAS, members of the University Management, Dean, Faculty of Pharmacy, Deans of other faculties, Head of Departments, or the Principal Officers of the University, distinguished participants, our keynote and invited speakers, members of the press, ladies and gentlemen. I warmly welcome you to the 4th conference of the Faculty of Pharmacy, University of Lagos. The theme of this conference is Translational Research and Strategic Partnerships, Advancing Pharmacy and Health Systems. The choice of this year's conference theme underscores the importance and the benefit of continued interdisciplinary collaborations, forming partnership with relevant external stakeholders to leverage on their strength and overcome challenges. By forming partnerships, we can share resources, knowledge, and expertise to bring innovative products and services to the market and improve public health outcomes. To give us a profound and accurate insight into the conference theme, we have the privilege of having Professor Duncan Kirk, the Dean of the Faculty of Science, University of Bath from the UK, as our keynote speaker. I warmly welcome you, sir. Thank you for joining us. Distinguished ladies and gentlemen, it is gratifying to note that the program for the two-day event covers a diverse range of very interesting topics, including patient-centered innovative drug delivery systems for enhancing healthcare, therapeutic outcomes, and translating natural products into therapeutic innovations, advancing phytomedicines from bench to bedside. We will have that on day 1. These presentations will be delivered by Professor Mohammed from Hassan Pharmacy School from Birmingham, from the UK, and Professor Amala Somnath from Oregon Health and Science University, all the way from the US. On day 2, I would like to draw your attention to the papers on medicinal chemistry meets translational research, innovations in drug design, synthesis, and delivery, and harnessing the microbiome for antimicrobial stewardship and resistant mitigation. These presentations will be delivered by Dr. Nte Kang from University of Bua from Cameroon and Professor Agbakoba from Nnamdi Azikiwe University, Akwa, Nigeria, respectively. Other sessions we address digital health and pharmacy transformation, transforming patient care, with technology. All these will be presented by Professor Baraka, an experienced academic from Fatima College of Health Sciences from United Arab Emirates. Ladies and gentlemen, it may interest you that we have well over 130 registered participants from academia, industry, and research as research students participating in this conference. And we'll be making different contributions during the parallel sessions. I have no doubt, and you always agree with me also, that the 2 days is packed full of opportunities to listen to seasoned experts and engage profitably. I'm confident that the presentation will be stimulating, engaging, and impactful. I therefore urge you to take full advantage of these sessions to connect and share experiences and explore potential collaborations. At this junction, on behalf of the Planning Committee, I would like to express my thanks to the Vice Chancellor and the University Management team for their continued support. My sincere appreciation goes to the former Dean of the Faculty of Pharmacy, University of Lagos, Professor Gloria Ayola, under whose tenure we started the planning of this conference, for our immense support and encouragement. I appreciate the current Dean of the Faculty for his immense support. My deepest gratitude goes to members of the Planning Committee for the tremendous amount of work done and the time spent in the organization of this conference. I also want to thank those that supported us, and some of them will be giving their presentation during this conference. I equally have directly and indirectly supported us during the planning stage of the conference. I thank you all. Last but not the least, my deepest gratitude goes to you for participating in this conference. Ladies and gentlemen, let me express on behalf of the committee our most sincere wish that the discussion and engagement resulting from this conference will positively contribute to your individual progress and impact our community. Once again, I welcome you to this conference. Thank you.
Thank you so much, the Chairperson, Planning Committee, Professor Margaret Shofidia. Thank you, ma'am. It's now time for the Dean's welcome address. The Dean Faculty of Pharmacy, Professor Sunday Adeshegun. You're welcome, Prof.
Thank you very much. I want to welcome everybody to this conference. Now the welcome address by the Dean, Faculty of Pharmacy, the Vice Chancellor and Chief Host, Professor Folashade Ogushola, OON, FAS, the DVC, Academic and Research, Professor Bola Obo, the DVC, Development Services, Professor Afolabi Leshi, the DVC, Management Services, Professor Falaye, the University Bossa, the Librarian, and the Registrar. I appreciate everyone for joining. Our distinguished guest speakers and keynote speakers, esteemed plenary speakers, the members of the university community, the past deans of the Faculty of Pharmacy, and our distinguished professors, and the gold medalists, the students, ladies and gentlemen. It is my profound honor and pleasure to welcome you all to the 4th Faculty of Pharmacy Virtual Scientific Conference of the University of Lagos. This year's theme, Translational Research and Strategic Partnership Advancing Pharmacy and Health System reflects a timely and urgent call for action. As pharmacists, scientists, healthcare professionals, we recognize that research must not remain confined in the laboratories, but must be translated into innovations and policies that will improve health outcomes and strengthen pharmaceutical practice, as well as safeguard our future. We are deeply privileged today to have with us Professor Duncan Craig, who will deliver the guest lecture and keynote address on our central theme. In addition, we are highly honored to host a rich array of plenary sessions that highlight the diversity and depth of pharmacy research across the globe. Professor Alfaz Mohammed will take the first plenary session on patient-centered innovative drug discovery system for enhancing healthcare and therapeutic outcome. We also have Professor Amala Solmala. We take the second plenary on translating natural products into therapeutic innovation, advancing phytomedicine from bench to bedside. We have Dr. Fidel Ketekan. I will take the third plenary on medicinal chemistry meets translational research, innovations in drug design, synthesis, and delivery. And the fourth plenary section will be taken by Professor Neka Regina Agbakoba, announcing the microbiome of antimicrobial stewardship and resistant mitigation. The fifth, but not the last, by Professor Mohammed Baraka, Digital Health and Pharmacy, Transforming Patient Care with Technology. We are grateful for each of you for coming to honor our invitation and for contributing your expertise to this important discourse. To our participants, the faculty members, the researchers, students, practitioners, stakeholders, I warmly welcome you. This conference belongs to all of us, and its success will depend on your active participation, thoughtful engagement, and partnership we build beyond these 2 days. I must acknowledge with gratitude our Vice Chancellor, Professor Folashade Okushola, for our visionary leadership and steadfast support to Faculty of Pharmacy especially, and academic excellence. Permit me also to especially appreciate the Planning Committee on behalf of Faculty of Pharmacy Management, under the able leadership of our indefatigable Professor Margaret Shovidia, for their dedication, sacrifice, tireless efforts in putting together this conference. Your commitment and hard work are truly commendable. As we begin, I invite us all to engage wholeheartedly, to share, to learn, and to create collaboration that will advance pharmacy, strengthen health systems, and improve lives across communities and nations. I welcome you once again, and I wish us a most rewarding and impactful conference. Thank you very much. God bless.
Another round of applause for the Dean, Faculty of Pharmacy, University of Lagos, Professor Sunday Adeshegun. Thank you, sir, for that address. Esteemed conferees, it's now time to declare the conference open by the welcome charge, which will be given by the Vice Chancellor, Professor Folashade Ogunshola, OON-FAS, ably represented by Professor Afolabi Leshi, DVC Development Services, who is currently online. Professor Afolabi Leshisa.
Good morning, distinguished participants. I hope you can hear me. Can you hear me? Hello?
We can hear you now.
Okay, if you can hear me, I will continue. Thank you very much. On behalf of the Vice Chancellor of the University of Lagos, Professor Folashade Ogunshola, OONFAS, I bid you a warm welcome to our University of Lagos, University of First Choice and the nation's pride, as we say in Nigeria. I want to use this opportunity to congratulate the Faculty of Pharmacy for another conference, the fourth in the series of faculty conferences, and with the theme of translational research and strategic partnerships, advancing pharmacy and health systems. Vice Chancellor would have loved to be here, but she's currently out of station and she's involved in quite a number of meetings in Abuja as we speak. And she'd love to be here. Pharmacy is very dear to her, as it is dear to a lot of us. The choice of your theme is very timely and very apt, as it aligns with the vision of the Vice Chancellor in bridging the gap between academia and partnerships and the community. And of course, Faculty of Pharmacy is uniquely positioned to deliver on translational research because we are in a part of the country that has quite a number of medicinal plants that can be translated to products. I also want to commend the faculty for the diversity and the breadth of the speakers who have been selected to address us at this conference. And it speaks to the quality that is available out there that we can tap from. Also, I would like to commend all the professors and all the faculty in the Faculty of Pharmacy for your continued dedication to delivering on the mandate of teaching, research, and community service. So on behalf of the Vice Chancellor, I'd like to wish us all fruitful deliberations. And with these few words, I would like to declare this 2025 fourth faculty conference open.
Applause for the Deputy Vice Chancellor, Managed Development Services, representing the VC on the opening charge. The time we have been waiting for now. The conference has been declared open. It's now time for the keynote speaker to speak to us. It's no other than Professor Duncan Q.M. Craig, the Dean Faculty of Science, University of Bath, United Kingdom. Dr. Craig, Professor Craig, kindly we are waiting for Professor Duncan Craig to join us. So now, before then, you'll be seeing our sponsors highlighted. Thank you for your patience. Thank you, esteemed Spirit. You know, with us now, Professor Duncan Q.M. Craig, the Dean Faculty of Pharmacy, University of Bath, United Kingdom. Professor Craig, kindly turn on your video while I read your citation. Okay, good to see you, Prof. Professor Duncan Q.M. Craig graduated with a Bachelor of Pharmacy honors degree from the University of Bath in 1984. Following pre-registration training at Upjohn Limited and St. Thomas Hospital, he went on to study for a PhD at the School of Pharmacy, University of London, on the topic of polymeric drug delivery systems. He subsequently joined the staff and rose to the position of reader in 1999, but left to take up a chair at the Queen's University, Belfast, where he stayed for 4 years before moving to the University of East Anglia to set up the new School of Pharmacy in 2003. The school went on to achieve top ranking in the National Student Survey for 5 years in a row and was consistently ranked within the top 3 UK pharmacy schools in the major league table under his stewardship. He stepped down as head of school in 2011 to work for the Vice Chancellor's office as Director of Internationalization, charged with shaping the university's policy on international relations and collaboration. In 2013, he returned to the School of Pharmacy, now part of University College London, to assume the position of director of the newly merged school. Professor Duncan has won numerous prizes, including the Glasgow Snickline International Achievement Award, the Controlled Release Society Young Investigators Award, and the British Pharmaceutical Conference Science Award. His research interests include the generation of drug-loaded nanofibers and nanoparticles, the use of new thermal analysis approaches for dosage form characterization, and the development of novel polymeric drug delivery systems. After 9 years leading the University College London School of Pharmacy, during which the school reached 5th position in the QS Global Rankings for Pharmacy and Pharmacology, he assumed the position of interim dean of the University College London Faculty of Life Sciences in 2022. He then moved to the University of Bath to take up the position of Dean of the Faculty of Sciences in March 2023. Here, he's leading on major projects, including the development of new buildings, the reshaping and strengthening of the departments in the faculty, and the development of new centers of excellence, which showcase the many strengths of the faculty. Professor Duncan Q.M. Craig, who is speaking to us on translational research and strategic partnerships, advancing pharmacy and health systems. Join me with a resounding round of applause to welcome our keynote speaker.
Thank you very much for that introduction. Do you wish me to give the presentation now? Well, first of all, can people hear me?
We can hear you, Prof, loud and clear.
Okay, that's wonderful. And do you want me to give the presentation now, or is this?
Yes, please.
Okay, will do.
Thank you.
Okay, you're very welcome. Right, so I've not used this particular version of Zoom, so I'm hoping the share is going to be friendly to me. Can people see that okay? Right, so there we go. So first of all, thank you very, very much indeed for the invitation to this meeting. It's a real pleasure, and it's it's been so good working with Urma at the time that she's been at UCL. So I'm very grateful and appreciative for the opportunity to speak to you all. I thought I'd take a slightly unusual approach to this presentation because I saw that the brief was about looking at strategic partnerships, which is something that's been hugely important to me throughout my whole career. So I'm really going to emphasize that, but I'm rather than just sort of give you a mass of science, I thought it might be more interesting, perhaps particularly for the people at the beginnings of their careers, if I did it as a sort of travelogue of what happened during my career and basically look at it historically in terms of how these various partnerships arose and what the consequences of them were. So I very much hope that that approach is going to be one that is going to go down well with the audience. Before I do that, I wouldn't be doing my job if I didn't tell you a little bit about Bath. You're probably all wondering where to go on your summer holidays, so hopefully this will provide you with an answer. So Bath is a town located in the southwest of England. It's very famous within, well, worldwide, but within the UK particularly. If you hear a fire alarm, it's just the test, so it will go away in a minute. It's about 80 minutes away from London on the train and very close to Bristol Airport and not too far from Heathrow. So it's very well located. But it's a World Heritage City. And it's very, very famous for its architecture. The council only let you build in this particular type of stone. So it's very, very beautiful. And basically, it's famous for its Roman spa. So when the Romans invaded Britain, they found a natural hot water spa and they built around it. And basically, you can still wander around the spa today. In fact, you can even drink the water. It tastes absolutely disgusting, but apparently it's meant to be very, very good for your health. And so it was famous for the time of the Romans, but then it became famous several centuries later in the 19th century, in the 18th century, because it became effectively a tourist town, and it was built up. And you can see here, assuming that you can see my arrow, this is the famous Royal Crescent. So you've got all these beautiful Georgian buildings, and it was very famous because a lot of our most famous writers came here to take the waters and to just gather and socialize. And it's well known as a very safe city as well. The student experience here, as you'll see in a minute, is very, very positive indeed. And also it's got a river that runs right the way through. Slight problem with that is it attracts a lot of seagulls, which have become a tourist magnet, basically, but they're kind of pests and they sort of follow all the boats going in and out. You can see a few of them if you look closely on the slide there. And it's also surrounded by beautiful countryside. So hopefully you can see why I was not unhappy to come back here. If you remember from the introduction, I actually did my first degree here in Bath. So it's a really, really lovely environment to work in. And just a little bit about the university. It's on the top of a nearby hill. It's repeatedly in the top 10. It was University of the Year, according to the Times, in 2023, I think. And we're well known for being what we call a dual intensive university, which is basically means that we try to be really good at teaching and research, not one or the other, but both. So our scores that we get from the students are very, very good, and that puts us in very good rankings. We do well in terms of the employability of our students as well, because we've got a very extensive placement system whereby we give them work experience during their degrees. And we've gone up 18 places in the QS ranking this year, up to 132, which we're very, very pleased about. And we've got the ambition of going to be a top 100 university. So a little bit about the faculty. It's a Faculty of Science, has chemistry, computer science, life science, which includes pharmacy, mathematical science and physics. And I just thought I'd mention, in case it's of any interest, some of the master's courses that we do. So we do master's courses in computer science, life sciences, and mathematical sciences. So that's stealing about 5 minutes from my keynote time, just to tell you a little bit about Bath. But I think it's quite helpful to get a little bit of context about the environment in which I'm currently housed. So to move on, please forgive me if I tell people things that they already know and they've known for years and years, just in terms of the introduction here. But I'm imagining that, you know, as we all know, pharmacy is a very sort of broad church. So I think some of you will be familiar with some of these basic concepts and others perhaps less so. So I'll just include it to try to bring everyone with us. So basically, one of the big problems facing the pharmaceutical industry is that many of the drugs that are being developed at the moment for oral administration have very low water solubility. And basically, just to remind ourselves, solubility is the equilibrium concentration of a saturated solution. It's related to dissolution, which is the process, whereas solubility is the equilibrium value. And it's the value that is measured as one of the first assessments of a new drug compound by the pharmaceutical industry. And we've got this conundrum that the drug has to be in solution before it can pass through any biological barriers, particularly the gut wall, but then it's got to be sufficiently lipid soluble to be able to get through the gut wall. So you're asking the drug to do two conflicting things. You're asking it to be water soluble so it can dissolve, but then you're asking it to be lipid soluble so that it can get through the gut wall. And most of the time we find ways of getting away with it, but very often this proves to be a big problem. And so this is where the formulation scientists come in, and they have to apply one of a series of possible approaches to try to overcome this conundrum, this contradiction. So the fundamental problem that you've got is that if you don't resolve this, then the drug is simply going to pass through the body and you're going to get low bioavailability. And when you have low bioavailability, it's also very often very variable, which obviously is not good for the patient because the plasma levels will be moving around. So for example, itraconazole, you don't need to have all that much chemistry to take one look at that molecule and to guess that it's not going to be particularly water soluble. So at neutral pH, the solubility is about 1 nanogram per mil, whereas at acidic pH, it goes up quite a lot to 4 micrograms per mil. So pH sensitivity is quite a big thing here. And of course, we have the famous biopharmaceutics classification system. It's fascinating if you go back to the original paper because it's pages and pages of equations all to get to this very, very simple idea of classifying drugs according to, are they permeable, are they soluble, are they both, are they neither? And basically, the classification that a lot of us have been working on is class 2 drugs. And basically, there's a low solubility but high permeability. So in other words, if you can get the drug to dissolve, then actually it will cross the lipid membrane of the gut reasonably well, if it's in this category. So therefore, it allows you to focus on the problem of trying to get this very, very low solubility drug to dissolve in the first place. And so what do we mean by poor solubility? Well, the definition keeps moving to get more and more pessimistic as more and more drugs come through with vanishingly small water solubilities. Just to give you some figures here, poor solubility is typically considered to start at about 0.1 milligrams per mil. Ibuprofen, which does get absorbed reasonably well, that's got a solubility of 0.021 milligrams per mil. But this is sort of old hat. I mean, a lot of the drugs coming through now have got solubilities way under 1 microgram per mil. And again, figures vary, but of the new pipeline of drugs coming through, it's estimated about 40% of them have this problem. So it's a big, big issue. And the reason for the two pictures there, one is that the pharmaceutical industry nickname for this kind of drug is brick dust. If you think of brick dust, it's not going to dissolve in anything. So that's a term that's sometimes used. And somebody with too much time on their hands worked out that a lot of the drugs coming through now have a solubility less than the statue of the Venus de Milo, or another friend of mine likes to say it's got a solubility less than the Taj Mahal. So you start to get an idea of how on earth are we going to get these drugs, which just do not have any measurable or virtually non-measurable water solubility, to dissolve in the aqueous fluids of the gastrointestinal tract. Well, the good news is that there's quite a few different approaches, from very simple ones like reduction of particle size. Formulating the drug as a salt has been used for decades. But the one that I'm going to focus on is solid dispersions, because that's what I started off with my PhD in. It's a very, very simple idea. You take your drug and you disperse it, typically by melting, it doesn't have to be, in a water-soluble polymer. And for reasons that people are still arguing about, you can increase the dissolution rate of drugs by orders of magnitude simply by dispersing them in these polymers. And I'll come back to what some of the mechanisms of that may be in due course. The fact is, though, that it works. So this is a fairly early study that we did, which unusually for us involved a human bioavailability study in collaboration with University Science Malaysia, where we looked at vitamin E, alpha tocopherol, and basically we were able to show that when we disperse that in a lipid type water miscible polymer, JDCF4414, you can see from the diagram here that the plasma concentrations compared to the existing commercial product were much, much higher. So these technologies, they really, really do work. And when I started my PhD, there was a lot of interest in these, but industry felt nervous about going down this path because one, it was difficult to scale up, and B, they didn't really want to invest a lot of money in something that people didn't really understand how it was working. So there was a lot for academia to do to try to increase that understanding. So here's the sort of beginning of the history lesson, as it were. So I did my PhD at what was then the School of Pharmacy, University of London. It was a separate college of the University of London in those days. And then I got this job called Teaching and Research Assistant, which I nicknamed Dog's Body Lecturer. It was a kind of very junior lecturer position, but it was wonderful. Because after my PhD, it gave me experience in teaching and also was a very, very useful step up into fully fledged academic life. And I stayed there up until 1998, where I'd risen to the position of reader. I don't know whether you have that position in Nigeria. It's being phased out now, but it's kind of the one below professor. So what I was particularly interested in was trying to understand the structure of these solid dispersions. So basically what you're doing is typically you are melting a polymer, you're mixing in a drug, and then you're solidifying it, or maybe you're spray drying a solution of the two. One way or another, you're getting this drug to go into the polymer. And you might think, well, there's only two things there. How complicated can it be? But actually, the idea was that if we didn't understand what the structure was and how the drug was dispersed, then it would be very, very difficult to understand the mechanism. And I became interested in looking at new techniques with which to study these systems. And so that automatically, during my PhD, led me to start working with solid state chemists and physicists and people outside the normal pharmacy arena, which proved to be very, very interesting way of looking at things. And I'll just mention one thing as well, that when you say that you're dispersing the drug in the polymer and then you're solidifying it, one of the questions I became interested in, which surprisingly hadn't really been addressed, really simple question. When you put that drug in the polymer, does the drug dissolve? Does it stay as solid lumps? Does it partially dissolve? And then when the whole thing solidifies, does the drug recrystallize out, or are the drug molecules all separate? And those sorts of questions in those days weren't really understood, but you can imagine that they must be associated with the mechanism by which the drugs show this rapid dissolution. So I'm not going to go into this in detail because it's something that I did during my PhD for a few years afterwards, but then kind of moved on. The big irony here was that when I was at school, I was terrible at physics. I really couldn't understand it at all. So I ended up doing half my PhD with the physics department at King's College London. I'm not quite sure how that happened, but they had a technique called dielectric spectroscopy, which is basically where you apply a field, an electric field to a sample. And all the dipoles in the sample, I'm going to use my pen here, the dipoles will tend to line up with the electric field. And then if you use an alternating electric field, the dipoles kind of move with the field. And basically you can measure that movement, and it gives you information about how mobile those particular molecules are. And it'd been used for semiconductors and polymers and quite a few things, but it was just starting to be used as an applied tool. And basically I wasn't the first, but it was, pretty early days for using it for pharmaceuticals. What was kind of amusing was that after I published a few papers in this, because it was a new technique, that got a bit of a buzz, and I was actually commissioned to write a book on it, which, of course, being young and probably a little bit arrogant or naive, I agreed to do. And of course, it meant sort of really scraping around everything that had ever been done on dielectrics with pharmaceuticals. I think it's the worst selling book they've ever had. I don't know how many copies that actually got sold. It's so specialist. I was amazed looking back that they commissioned me to write it. But every now and again, I get an incredibly small check from the publishers, which probably costs them more to send and prepare the check than it does what was the value of the check itself. But not to worry. So I started looking at that. And again, that brought me into contact with physicists, and I started going to physics conferences, which was really interesting just to get this different perspective on how people in different fields think. And another area that I worked on a lot was thermal analysis. And basically, this is, as many of you will be aware, this is where you apply a heat signal to a sample and you measure the response. And the easiest example of that is simply measuring melting. You measure the temperature, but also the energy at which a particular material melts. So the standard technique at the time was differential scanning calorimetry, where you heat up your sample pan and a reference. And as I say, when you get to a particular thermal event, such as melting, or if you're cooling, you get to crystallization. You measure the temperature at which that occurs, and you also measure the energy. And from that, you can extrapolate a load of really useful information about the structure of your sample. So a really obvious one would be, well, is the drug crystalline? Well, if it's crystalline, then it will melt. Although even that's not quite as straightforward as you might think, because if you've got a polymer and a drug, then when you heat the two of them up, the polymer will tend to soften, and the drug may well actually slowly dissolve in the polymer as you're heating it up. So again, it's one of these things that even though it sounds as though it's going to be really simple, it develops its own complications all by itself. So one of the things that was coming out at the time, and the story behind this was I went to a one-day conference at Birkbeck College, and basically it was a whole load of solid-state chemists talking about various calibration techniques. So it was a little bit dull, to be honest. But right at the end, the very last speaker was a guy called Mike Redding. And he basically said, well, what we've all been doing over the years is heating up our samples at 5 degrees a minute, 2 degrees a minute, whatever, in a straight line. So this is the dark red line that you see here. Temperature goes up with time at a fixed rate. And what he was proposing was, he said, there's another way of doing this. You could actually have the temperature going up, but instead of going up linearly, you could get it to go up as a sine wave. And basically, I thought this was a really, really interesting idea, because obviously I've been doing all the work on the dielectrics, which had involved sort of, sine waves and alternating fields. And I'd also been doing some work with rheology, where there's the same principle if you use oscillator rheology. But I hadn't come across this in terms of doing a heating signal. Now, the obvious question that I should have asked myself at the time, but it took me a couple of days for this to filter through, is this is all very flashy and new, but why would you want to do this? What's the advantage of doing it? Well, essentially, what you do is you can split the heating signal that you get into different components. And I'll put this, at the risk of oversimplifying it, I'll put it very simply, but if anybody's interested, I can go into more detail. Whenever you heat something up, then you're always going to have a heat capacity. The heat capacity is the amount of energy that you need to raise the temperature of something. So water's got a very big heat capacity. Why it takes a long time to boil a kettle, for example. It's a value associated with the material, and you can link it to all sorts of different properties, entropy, etc., if you so wish. So that's always there as a kind of baseline. But then when you get to something like the melting point, then you've got an actual kinetic event. And normally with DSC, what you do is you measure both of those two things together. You can't separate them out. But by looking at the sine wave and analyzing the sine wave, you can actually split that signal so you can see the heat capacity in isolation. And that can be very, very valuable for reasons that I'll explain in a minute. But the point is that when you do modulated DSC, you kind of get three signals out from the same measurement. You get the total signal, which is the same as the DSC, and then you get these two components, the heat capacity signal and the signal associated with any thermal events such as melting or crystallization. So why would you want to do this? Well, by a really, really happy coincidence, around that time, there was a massive explosion of interest in the pharmaceutical world in amorphous systems. So essentially, most of the materials and certainly most of the drugs that people were dealing with would be crystalline. So you've got your unit cell, which repeats itself in an ordered way. But you can also have drugs and obviously polymers as well. In fact, sometimes especially polymers. You can have them in the amorphous state, whereby basically they have no long range order. So the molecules are arranged kind of higgledy-piggledy. So essentially, for a polymer, it's a bit like thinking of a big bowl of spaghetti, where basically it's been mixed up and it's not ordered. And these particular materials have some very, very unique properties. And the field was starting to realize that we'd been ignoring this for too long. And actually, this could explain quite a few things that we were looking at, including solid dispersions. Because if you remember, I did sort of say at the beginning that one of the questions was, is the drug actually molecularly mixed in with a polymer? Is it crystalline? And the answer seems to be, in many cases, it's actually molecularly mixed in. So if you've got a polymer which doesn't crystallize, and many of them don't, you've got an amorphous system on your hands. And that's not going to obey the same rules as you get with crystalline systems. So very briefly, and again, apologies to people that are familiar with this already. If we start off here with a crystal, what happens is that you heat the crystal up and you get to the melting point. And then I've done this as volume. It's the easiest way of thinking about it. You get an expansion because all the molecules are now much more mobile because it's melted. And basically, it continues to expand through the liquid state. And so what should happen is you should then cool it back down and it should recrystallize and you go back to the crystal. However, what very, very often happens is that you keep cooling, but depending on how fast you cool it, it doesn't actually crystallize. Crystallization takes time, so you can avoid it. And basically, you can keep in this supercooled liquid state, but it doesn't just follow this dotted line here and just shrink and shrink and shrink. You get to a point whereby suddenly the molecular mobility goes right down. So in other words, what happens is that when you're here, you're dealing with something that looks very much like a liquid. And then suddenly you get to a point whereby actually it feels more like a solid. It's not a solid, it's actually a glassy state. It's still disordered. But because the molecular mobility is so low, that then means that basically you can snap it, basically. It feels as though it has the properties of a solid. Now, why does this matter? Well, one of the reasons in the solid dispersion field that it really mattered a lot was that if you have a drug dispersed in an amorphous polymer as an amorphous solid dispersion, the big danger is that the thermodynamically stable state for that drug is actually the crystalline state. It's not this state at all. So over a period of time, in theory, the drug can actually crystallize out. So being able to predict that became really, really important. And one of the things that was massively important was to be able to measure the glass transition temperature, this temperature at which the system goes from this very rigid state to the more rubbery state here. And this is actually rubber from a rubber tree. And a lot of the knowledge and the study that came was actually from both rubber and also attempts to mimic rubber by using synthetic polymers. So this really came from the polymer sciences. So in terms of your drug stability, if you're in this region, you're in big, big trouble because basically the molecular mobility is high. The drug molecules can get together really easily to crystallize. But you're not out of the woods. If you're in this state here, it can still recrystallize, but much, much slower. And there's various clever things that you can do in order to predict that. But the key thing you've got to do is you've got to know what this glass transition temperature is. But the thing is, it's not like melting or crystallization, which is a big energetic thing where you're forming or breaking bonds. You're not forming or breaking bonds. You're just looking at a decrease in molecular mobility. And that is related to the heat capacity. And if you remember a minute ago, I said that what the modulated DSC can do and is very good for is looking at changes in heat capacity. So this is one of the first studies that we did, which was the drug saquinavir. And this is what I meant when I said that you can get 3 signals out, or you do get 3 signals out. So this is what you'd see with a normal DSC. And it looks like a melting, but it's not a melting. It's in fact a glass transition. If you look at this yellow one, that's called a reversing heat flow, but that's the heat capacity. And basically, the glass transition is characterized by this very, very subtle change in the heat capacity. So with a conventional DSC, this one, you wouldn't see it at all. Now, you might be confused at this point and think, well, what on earth is this? This is the bane of people's lives. This is called an endothermic relaxation. And basically, to put it as simply as I can without spending hours on it, when you store a glassy material, basically it tries to relax. It tries to go back to its ground state, and it can't. It gets trapped. So when you go through the glass transition, it overreacts, and it actually lets it undergoes a relaxation process. A friend of mine described it as if you tie somebody up really tightly with rope, and then you cut the rope. They sort of go like that. They kind of overcompensate. That's kind of what the system is doing. And this was causing masses of confusion because everybody was thinking it was a melt, which meant that everything was crystalline, but it wasn't. So modulated DSC started giving us an insight into how these systems were working. And it was, this technique came along just at the right time because people were really starting to talk about these questions. So anyway, just to go back to the history. So I was at the School of Pharmacy for quite a long time. And then things were really starting to happen in Belfast. Now, when I was growing up, Belfast was a place where you would be very nervous about going to because of all the troubles. But basically, in around 1999, there was really good progress being made of the Good Friday Agreement, which was the peace agreement, which still, by and large, is holding now, I'm delighted to say. But also it was attracting a lot of interest to Belfast, and people had forgotten what a fantastic city it was and what a fantastic university it had at Queen's University Belfast. So basically, I took my first professorship or chair at Belfast, and half my friends thought I was completely mad, and the other half thought that's a really, really smart move because Belfast is really going places. So I had a really, really good time there for about 4.5 years. The group, almost all of them moved over with me as well. So I basically had a sort of support system, which was hugely valuable. But also I had another toy to play with around that time. So the same guy that did the modulated DSC, Mike Redding, who is by now a close collaborator, he's a solid state chemist, but very interested in developing techniques. So his next project was to combine atomic force microscopy with thermal analysis. Now, with atomic force microscopy, you're probably aware you have this very, very fine tip that moves over a sample, and it can measure the lumps and bumps or the topography of the sample, and you can get exquisitely detailed information. But what this technique does is it replaces that tip with a little heater. So what you're doing is you land on an area and then you start heating, and then when the material underneath it softens, then the probe will sink into it. So it's now combining spatial information with thermal information, which is normally very difficult to do. You've got things like hot stage microscopy, but that will only look at it from a few micrometers. This is starting to go down into the nanoscale of allowing you to interrogate samples on a point-by-point basis. And of course, one of the things about pharmaceuticals, if you think about it, if you think about a tablet, we have no idea where anything is in that tablet. We compress it, but we don't know, it just looks like a shiny, hard white surface. But basically what you've got is you've got all your different excipients basically spatially arranged somehow. And we don't really have many techniques that can look at that. And of course, it's also very relevant to solid dispersions. So from this very simple idea, a whole load of different ideas came out, things like three-dimensional imaging and nanoanalysis. So it really sort of like opened up a whole range of possibilities of actually understanding not just physical structure, but where that structure was and identifying different structures. So with a nanothermal analysis, one of the problems with the earlier model was the tips were actually quite big, so you didn't have the resolution. But with nanothermal analysis, the Georgia Institute of Technology developed these very, very fine tips. So that kind of like brought us into a new generation of being able to look at samples, not at the same scale that you can do with conventional atomic force microscopy, but you can certainly go down to a few nanometers. So this is looking at ibuprofen, for example, and basically we managed to get down to about 400 nanometers. And this basically shows what happens to the probe. You heat up. Because you're heating, then the probe is lifted up slightly because the material expands. And then when it melts, you basically the probe dives in. And so this is an image taken after the experiment where you can see this sort of tiny little bullet hole in your sample. So we're quite excited about this because it was enabling us to start looking at things spatially. So I'll come back to the next generation after that in just a minute. But then in 2003, in the pharmacy world in the UK, we heard these rumours that the University of East Anglia, who had a well-established chemistry department, were looking to set up pharmacy. And of course, setting up a new pharmacy school in those days was unheard of, basically. There hadn't been any new schools for decades and decades. But basically, the idea is, what about setting up a joint school with chemistry at East Anglia? There are no other pharmacy schools around there. It was very difficult for employers to find people to work there. So there was a very, very strong workforce argument because this is right at the east end of the country. It's quite remote. And basically we thought, oh, this is interesting. I wonder which mug is going to end up heading that up. But I thought I'd throw my hat into the ring, and I ended up getting the job of being the head of pharmacy there. So we were so enthusiastic, and we actually had a very small student group. So actually we got to know the students really, really well, and all the staff were totally dedicated to this new project. And that was reflected by, all these surveys, and like the National Student Survey, where we kept annoying everybody else and coming top in it one year after another. So that was great. So that was a very exciting time. And again, the group moved with me from Belfast, and of course, new members joined since then. Around that time as well, the technique of hot melt extrusion was starting to come through. And that was overcoming one of the major worries that the industry had. And that is, how do you make these solid dispersions at a large scale? Well, with hot melt extrusion, what you have is you have these twin screws. You have a feeder, you put the polymer and a drug in, and basically it does all the work for you because this is all heated, so it's in the liquid state. And then these screws, by pushing the material through, intimately mixes it. So you end up with this wonderfully very, very good mix of the drug being dispersed. So for example, if you went to a conference and they were demonstrating one of these instruments, then they would actually have a small amount of dye, like dark blue crystals, and a white polymer. And instantaneously, what would come out would be this beautiful light blue extrudate at the end, where you couldn't see any evidence whatsoever of any drug crystals, and it had just come out in a matter of seconds. So you can get benchtop ones of these. So we got one, and that really sort of added a new dimension to our work. And I've said here, mark the start of the move towards engineering. This was really the territory we were starting to go into, but there was no engineering department at UEA, which for me was a bit of a shame. So I was kind of like acting a little bit alone, but I'd have loved to have worked with engineers. But I worked with engineers in the manufacturing companies. So going back to the microscopy thing that we were talking about, if you remember that what you could do with these new nanotips was to measure a particular point, and then you could basically melt or softening temperature assessment at that particular point. So what if you got your probe and you just went and a big sort of pattern right across the sample? And this technique allowed you to do that automatically. So in other words, you were doing a 2D scan on the sample, but making hundreds of measurements to allow you to actually measure the surface of the sample as a whole. And so that proved really, really good for the solid dispersions, going back to this question of, is it really mixed in or not? So this is cyclosporin dispersed in the polymer eudragite EPO. under different mixing conditions. And what you can see here is that fairly clearly it's not homogeneous. And that's because you haven't mixed it vigorously enough to get the drug to disperse properly in the polymer. But as you change the mixing conditions, you can then actually get a beautiful, clear dispersion. So this was quite a nice demonstration of the sorts of things that you could do with it. And another one, which I thought was going to be huge, but kind of seemed to die a death a little bit, I'm not quite sure why, was a thing called photothermal microspectroscopy. And to cut a long story short, what you can do is if you put a very, very small amount of a sample on one of these probes, and then you shine a laser on it, and you tune the laser to different frequencies, you can actually measure the temperature fluctuations as a function of the frequency. And that's basically how IR works. So in other words, you could take a sample, you could put a little bit of, you could put it on a probe, and with that tiny, tiny sample, you could actually get an IR spectrum of it. And just to give you an example, one of the things that we became very interested in was how could you tell whether a new drug is stable or not when you've only got a few milligrams right at the beginning of its production life cycle. So what we did was we started with nifedipine, and you may remember that nifedipine is famous for being very light sensitive. So what we did was we put a 5 micrometer particle, just a single particle of nifedipine on the probe, shone the laser light on it, and then subjected it to UV light for periods up to an hour. And what we were able to do is we were able to track the degradation of the nifedipine because of the UV light shining on it with just a single particle over the hour. And we could do kinetic analysis and all sorts of clever stuff from that. So we got quite excited by that, but I think I don't know. I think the manufacturing companies or whatever couldn't quite work out whether it was a thermal technique, a spectroscopic technique, or a pharmaceutical technique. So it kind of didn't go anywhere. But it was great fun to be working in that area at the time. So moving on. So when I was at UEA, there was a massive row going on at the School of Pharmacy, University of London, the place where I did my PhD. Because you may remember I said that it was an independent college of the University of London. So the dean there was effectively a vice-chancellor. However, it had been suggested for many years that it should consider whether to merge in with University College London. Now, UCL is, you know, a world top 10 university. It's a huge university. Within, you know, the UK, I think, you know, you'd say that there was Imperial College, University College London, King's, Oxford, Cambridge, Manchester. Those, I would say those are the big six. So, I mean, it was, you know, a real giant. And half the staff at the School of Pharmacy wanted the merger, and half of them were absolutely dead set against it. And it was very, very divisive. And, you know, because I was a former member of staff there, I was sort of asked for opinions about things. And we all felt very sad about the fact that this was sort of so fractious and so, there were so many unhappy people there. And I was sort of thinking, well, if the merger does go ahead, I don't know what idiot is going to take over it. And of course, you can probably guess that idiot turned out to be me, because I got the phone call in 2012 saying, is this something that you'd be interested in applying for? And I nearly burst out laughing and said, no. And then I thought about it and I thought, well, actually, it could be fantastic because UCL is such a good university. So I applied and got the position. And, you know, there were so many good things going on within the School of Pharmacy, but also being in a university like UCL was a bit like being a kid in a sweet shop. There are collaborators everywhere, very much including engineering, which I'll come to in just a second. So the first morning was absolutely horrible. I just wanted to run outside and scream. Nothing seemed to work. They couldn't even get around to sort of replacing the light bulbs in lifts and things like that. It was just totally dysfunctional because all their energy had gone into these rows. But of course, it got much, much better. And also, I think one of the big fears that they'd had about the merger was that they were going to end up with a new dean who basically knew nothing about pharmacy, cared nothing about pharmacy. So whatever they might think of me, the fact that they knew me and they knew that I was a pharmacist came as an immense relief to them. So I had that on my side. So actually, I had a lot of staff support. And of course, the group came with me again. So I had a bunch of people that I could, use as a kind of sanity check resource as well. So things got better and better. And this is after I left, but it's now 4th in the QS rankings for pharmacy and pharmacology. So it's really done well under UCL. I can't take all the credit. But as I say, kid in a sweet shop in terms of the collaborations. There were so many exciting possibilities in engineering and in chemical engineering and in mechanical engineering and in chemistry and within the School of Pharmacy. As you'll see later, I started working with people like the gene therapists within the School of Pharmacy and also gene therapists elsewhere. So basically, it's collaboration heaven there. So I tried to take as much advantage of that as I could. Obviously, having the day job of being dean of the school, that ate into the research. But as I say, my research group was wonderful and were able to sort of work under their own steam to a very large extent. So that seemed to work out very well. And I think we came out with some of the best work in my career during that phase, even though I did have this big job of being dean. And one of the things that we got into was nanofibers. And basically, these are exactly what the name suggests. So these have been used for years in the biomedical field for things like tissue engineering. Basically, they are fibers of nanoscale width and diameter, and they hadn't really been used very much for pharmaceuticals. And one of the big reasons for that, which has now been overcome, is that it was quite difficult to scale up. So the industry would say, that's fine for making a few milligrams, but we need to make tons of product. So that, it's not really of interest. So one of the things that we were interested in is, one, are these things any good? And two, is there anything that can be done to address this scaling issue? But it did occur to me that if you had a nanofiber solid dispersion, i.e. a poorly soluble drug in a water-soluble polymer, you're going to have a massive surface area there. So actually, you should get some sort of massive supercharged high dissolution rate system, even with very poorly soluble drugs. So that was really where I was coming from, and the idea of putting drugs into them. And one of my key collaborators was a guy called Mohan Edrasinghe in mechanical engineering. And he was lovely. He was very much, I've been saying for years we should have a School of Pharmacy in UCL. It's so brilliant that you're here. And yes, I'd love to collaborate. And it was a hugely successful collaboration. We had many government grants and several postdocs and PhD students between us. So the fundamental technique here is a thing called electrospinning. And what happens there are many variations on this, is you have a polymer solution which you place on some sort of pump system. And basically you place a voltage from the tip to a receiver. And what happens is that basically as you push the syringe and push out the liquid, the voltage breaks down the surface tension and you get this jet flying out of liquid. And it basically flashes off the solvent in flight. And so you end up with these solid fibers. So one of the things that Mohan was working on was an alternative, which is called pressurized gyration. And the idea here is that instead of having an electric field, et cetera, which kind of limits things in terms of scaling, forget all that. Basically, have a drum with a whole load of holes drilled in it, and then you apply high pressure. So you're pressurizing the liquid, and then you spin the drum very, very fast. And by spinning the drum, you force out the liquid through the holes, and you get the same effect. You've got this jet of liquid which dries, and you then have a collecting vessel around it. So we got very excited about this as an alternative. And basically, I think she may have spoken at this conference, Bahija, Remy Abraham, who's now doing really, really well at King's. So she was a PhD student with me and then a postdoc, and she worked on this. And basically, her work showed that, first of all, we could make suitable fibers from the sort of polymers we're interested in, such as polyvinyl pyrrolidone. But also the dissolution rates were really, really good. So we were able to show that we got this lovely fast dissolution from these fibers. We went on in the collaboration to do something which again, I thought was very neat as an idea. The idea very much came from Mohan and one of his postdocs, but I helped with putting drugs in. But I don't know whether you can see, but basically the idea was to develop a handheld nanofiber generator, which could spray onto, for example, a wound. So if you look here, this is a mock-up wound, and you can see this sort of like white, almost sort of spider's web. And this is basically the nanofibers forming a mesh on the skin. And we thought, well, this could be a really good way for accidents, or using it in the field, maybe going around to people's homes to treat diabetic ulcers. So we got quite a large grant from the government to develop this. So this was another sort of really nice development from some of these ideas. I still kept my interest in analysis, and two of my colleagues at the UCL School of Pharmacy had done something really neat. That what they'd done was that they'd one of them was into DSC and the other one was into synchrotron X-ray diffraction. So what they'd done was they got together and they'd modified a DSC. They basically punched a hole in it so that a laser could go in and shine on the sample and then actually be collected by the synchrotron X-ray diffraction. So in other words, you could heat the sample up and get all your DSC data, but you could also get X-ray data in exactly the same way and overlay one on the other. So we were working with a drug, olanzapine, which you may be familiar with. It's quite complex. It's got 3 anhydrous polymorphs that were recognized. And it does a whole load of weird stuff like forms solvates with all sorts of solvents, etc. And there's a lady, Sally Price, in chemistry, who's a computational modeler. And she was working on this drug and several others because she's now a fellow of the Royal Society, which is very, very good at what she does. And basically her idea was if you could take a structure and predict what polymorphic forms, what crystal forms that structure could potentially make, that would be massively useful for the university, for the pharmaceutical industry. So anyway, what we did was we started looking at solid dispersions of olanzapine in PVP. And what we were able to show was that we made the solid dispersion. And essentially what happened was at about 110, the drug started crystallizing out as the polymer heated up and got more fluid and allowed the drug crystals to, allowed the drug molecules to come forward into crystals, and then it would melt. Fine. So that's quite nice to be able to do the X-ray diffraction at the same time. So the top is obviously the X-ray diffraction, the bottom is the DSC. However, what was strange was that when we looked at the X-ray diffraction patterns, they didn't correspond to any of those polymorphic forms that have been recognized. So what's going on? Is this a new polymorphic form? And then if you look at what Sally Price was doing, who is a collaborator in this work, she'd actually predicted there should be a form 4 using her computational modeling. And she was able to predict what the X-ray diffraction pattern should look like for that form 4. And lo and behold, what we found was that the X-ray diffraction pattern that we were getting and her predictions matched onto each other really, really well. So we got really excited about this because we thought, oh, we found a new polymorph for a drug. You know, maybe we can patent it and become incredibly rich. But the patent people turned around and said, oh, you've got to demonstrate it's got better bioavailability, do 5 years of work, you know, and we thought, no, we can't be bothered with that. So we just went ahead and published. So maybe that was a bad move. Maybe I should have waited and I'd be on a yacht somewhere by now. But anyway, it was a fascinating study. And what was also interesting was that the way in which the molecules were packed together for this form 4 was completely different to forms 1, 2, and 3. It's a completely different motif. So those of you that are into crystallography, you'll probably be able to appreciate these differences a bit more. But again, it was a lovely combination of analytical X-ray diffraction and computational modeling. And again, it's working across these different disciplines that gets you to where you want to go. And then the last example is microfluidics. So this was a friendship and a collaboration with chemical engineering, particularly Asterios Gavrilidos. And basically he grabbed me after a meeting and said, oh, I know you're friends with Mohan. We're doing some work with microfluidics. And, you know, we'd be very interested in doing some pharmaceutical studies. So basically what microfluidics is it's a broad term that it's like lab on a chip in some ways. It's using very, very, very controlled flow of very narrow channels of liquids in such a way as to control chemical or physical reactions. And these can be chips or they can be reactors, and I'll show you some examples of how this works. But it's becoming quite fashionable within the pharmaceutical world now, because there's so many different things you can do with it. But this also coincided with chats with colleagues both within the School of Pharmacy, but also in the biological sciences, over gene therapy. And I must admit, I don't want to sort of set a bad example, but a lot of this took place over a beer and down the pub. But that's where a lot of good things get going. Basically, these were two friends. And I was sort of saying to them, well, how do you actually make these gene therapy systems? And they were basically saying, well, we sort of mix them together and give them a jolly good shake. And then we start injecting them into whatever. And I was saying, well, how controlled is the manufacturing? And they both, they were staring at me as though I had two heads. So it then came to this idea of, could we actually start looking at the way in which we make these gene therapy delivery systems? Now, as you know, I don't think I need to sort of introduce gene therapy too much, but you have viral vectors, which are very effective, but they are a source of worry for safety because of potential immune reactions. And you've got non-viral vectors, which basically you don't have those same immunogenicity problems, but in a lot of cases, they're not as effective. However, we were getting interested in nanogels, and basically these are exactly what the name suggests. These are very, very small hydrogel systems with a cross-linker. And basically there's a lot of things you can do with these. They're attracting a lot of interest, very versatile. You can load them up. The difficulty with them is that they do tend to be pretty delicate. So, we've done some in vivo studies and they're not brilliant as far as whizzing around the bodies prepared. But basically the traditional way of making them is you take a polymer and a cross-linker, you mix them, and then that produces your nanogels. And so what we were interested in doing was developing them by microfluidics. So we used this reactor system whereby we put the cross-linker and DNA in one tube and then the polymer in the other, and then you got this mixing by diffusion by getting the pressure right by which you were introducing the two. And big shout out to Zoe Whiteley, who's an amazing PhD student now working for GlaxoSmithKline, who really pioneered this work. And basically what she did was she started putting plasmid DNA into these systems, got these very uniform, very well-controlled nanoparticles out. And basically what she was able to show was that if you then looked at transfection studies, you could demonstrate that depending on the composition that you had, you could actually get very good take up into cell lines from these nanogels. So we were very excited about that, and that research program has had more PhD students rolling on after it and is still going. So again, it's another example of how you've got. I mean, Zoe comes from the same background as me. She was an undergraduate, and basically. We were able to demonstrate that this was a way not only of making controlled non-viral vectors, but also a way of getting material into cells in a controlled manner. Sorry, I said the other thing that we did with microfluidics is looking at nanocrystals. And this is pioneered by Sharouk Abu-Khamis, who's now a lecturer at Hashemite University in Jordan. And basically, this led to a very large EPSRC government grant with the chemical engineers. And again, she used a reactor and she was able to basically get the nanocrystals to crystallize out in a very, very controlled way by mixing a drug solution with an anti-solvent, which is in principle a standard way of making nanocrystals. But this was done, as I say, using microfluidics, and we were able to get very, very high uniformity. And we were able to show that the dissolution profile for a commercial suspension and for our system were very, very similar using the nanocrystals. So as I say, that then led to this big grant with chemical engineers. And I'm not going to go through this in detail, but this is my very first AI machine learning paper. You'll note that I'm right in the middle of the authors here, so I'm not going to try to take too much credit for it. But basically what the grant was about was, can you actually have a feedback loop using machine learning whereby you can get even better control of the size by feeding back the size that you measure as it comes out, looping back, and then adjusting the parameters to optimize. So that project coming to an end, but it's been fascinating working with the engineers. So as was mentioned in the introduction, I actually did my undergraduate degree at Bath, so I never thought I'd end up in the same place where I studied, but I'm very pleased to be here. It's a really exciting and supportive environment. I would like to absolutely acknowledge the fantastic people that I've worked with, the collaborators, but also the research group who have kept me sane for so many years. And you know, without them, none of this would have been possible. Obviously, the sponsors as well. I'd like to acknowledge them. And I'd just like to finish with yet more pictures of the group. You probably get the impression that we do nothing but eat. This was a sort of like a dish party whereby each of these flags represent the nationality that the person's come from. There's Bahija as well. If you, I think some of you will know her as well. And hidden over here is actually Unama as well from one of the Christmas meals. So I hope that's been of interest. And depending on obviously what the chair would like, I'd be very happy to have any discussions with people if that's appropriate. I'll stop sharing now. Thank you very much.
Thank you so much, Professor Duncan Craig, for that detailed, insightful, and brilliant lecture. You all will agree with me that he's an expert in the generation of drug-loaded nanofibers and nanoparticles for the development of novel polymeric drug delivery systems. But first, we want to thank you, Prof, for taking us to Bath, United Kingdom, and back in a jiffy. Thank you for that. We now know that Bath is the UK's only UNESCO World Heritage. So, what we learned from this is that it led us to understand that when you have a drug that is not very soluble mixed with a polymer, it took us down the techniques that we use and what happens in the matrix to know how to achieve the solution and bioavailability. So he took us to different new techniques up to AI, basically machine learning. We appreciate you, Prof. Now, before we give him the award, we have to take the question and answer first, starting with those on the Q&A box. Prof, please. There's a question in the Q&A. Okay, it's not written. I can read for you. I thank you, Prof. Duncan Craig, for a very informative keynote address. A lot of lessons have been learned. Now the question is, how do we break through into gene therapy as a pharmacist? How do we break through into gene therapy as pharmacists?
That's a really good question. I think that gene therapy, the pharmacist clinically definitely has a role here. So one of the things that's happening in the UK, for example, is that we're starting to see pharmacists specializing in handling gene therapies. So, for example, Moorfield Eye Hospital, where, as you probably know, I mean, treatments of the eye are one of the areas whereby gene therapy has had some notable successes. They have pharmacists there who are looking after the storage, the procurement, the administration, the stability, all the science stuff around gene therapies. That's being done by clinical pharmacists. And I think, you know, one thing as pharmacists we need to bear in mind, where we are about the only healthcare professionals that have a really strong science background that enables us to actually understand how these very complex systems are working. You can have molecular biologists. I mean, the two people that I worked with. One was a molecular biologist and one was a geneticist. And then Zoe and I were the pharmacists. They knew all about the gene therapy side of things, but they knew nothing about, manufacture, about storage, about uniformity, about what would be acceptable to the pharmaceutical industry. As pharmacists, we have that knowledge. I think that where partnerships come in is that rather than trying to invade somebody else's territory and say to a geneticist or a molecular biologist, well, I'm going to gen up on gene therapy and I'm going to know more about it than you are, we can use the unique skills that we've got, that we obtained during our degrees and our experience following our degrees, to really contribute. So I think it's an area whereby partnership is absolutely brilliant for pharmacists. And more hospitals are setting up gene therapy units, and pharmacists are being involved in all of them in the UK. So I don't know, whether that's a worldwide phenomena, but it's lovely to see us using our science in this new clinical role.
Thank you so much for that answer. We have another question here, and it says, thank you, Prof, for this insightful presentation. I want to ask if plant extracts obtained from natural sources, for example, leaf extract, can be loaded on any of these discussed drug delivery platforms. For example, the electro-spinning techniques.
Yeah, the answer is yes, and people are doing that. I've seen some papers recently whereby people have taken extracts. I mean, all of the techniques that I was talking about in terms of preparation and presentation, there's no reason why they can't be used for natural products and materials derived from natural products. So there's no exclusion from that. So yeah, if you're interested, I definitely read a paper recently whereby somebody was taking I can't remember what the plant was, but it was definitely a plant extract and electrospinning it. It seemed to work perfectly well.
Thank you so much. A round of applause for Professor Duncan Craig. I hope that we are networking. Before we take the... Oh, okay. Somebody wants to ask another question. That's the final question, please, for our keynote speaker. I read. Thank you, Prof, for this stimulating talk. My question is, do we have commercially available and clinically used drug products based on this drug delivery technology? That's currently. Do we have commercially available and clinically used drug products based on this drug delivery technology?
The answer is yes, particularly the solid dispersions. So there are now several products on the market. The solid dispersion technology can also be used for controlled release as well as immediate release. So some of the products, particularly with the advent of hot melt extrusion, well, hot melt extrusion has been around in engineering for years and years and years, but it's relatively recent within pharmacy. So that's really sort of like opened up a lot of possibilities. And yeah, I think if you do a scan of the literature, pretty much all the systems that I talked about, there are commercial products available. They're specialist products because I think, my golden rule is that the pharmaceutical industry will only move away from a round white tablet if it absolutely has to. But there are many drugs coming through now where you have to use these more innovative technologies. Otherwise, you'll never reach the market. And you do wonder how many drugs have been rejected that could have been really useful for patients, because the companies just gave up on them and didn't try to use these technologies. I guess we'll never know. But yes, pretty much everything that I've been talking about, there are examples on the market.
Thank you so much, Prof. This brings us to the end of the question and answer. It's now time to present keynote speaker with the award. We have a plaque for you. It's ready physically, and it will be delivered to you in the United Kingdom. Thank you, Prof. Hold on for the presentation by Professor Bolajoko Aino, the Professor of Clinical Pharmacy. Prof.
Lagos Faculty of Pharmacy present this plaque to you, Professor Duncan QM Craig, as our guest speaker at our first Faculty of Pharmacy Virtual Scientific Conference with the theme Translational Research and Strategic Partnership, Advancing Pharmacy and Health Systems on this day, 10th September 2025. Thank you so much, Prof. We surely get this latest next month in UK.
Thank you so much.
Thank you so much, Prof. Another round of applause for Professor Bolajo Kaino for presenting the plaque to our keynote speaker. It's now time for company presentation. Yes. Because we have taken it already before he came, we are now taking the next plenary speaker, the first plenary speaker, Professor Afzal Rahman Mohammed. He is going to speak on patient-centered innovative drug delivery system for enhancing healthcare and therapeutic outcomes. And before we listen to him, I'll call on Dr. Kehinde Salako to read his citation where his video is turned on. Thank you.
Afzal Mohammed is a professor of pharmaceutics and associate dean, research impact and knowledge exchange at Aston University. He is an internationally leading scientist and a key opinion leader in particle engineering and pediatric formulation development. His research interests include the formulation, development, and optimization of orally disintegrating tablets, oral liquid nanomedicines, particle engineering through controlled dry particle coating technology, and development of cell culture-based models. Afzal Mohammed is the lead inventor of the patented novel dry particle coating technology. He set up Aston Particle Technologies Limited in July 2016 to industrialize the technology. The translational interface of his research is funded by grants from various bodies, including MRC, EPSRC, BBSRC, and NC3R, as well as Pharmaceutical Industry and Innovate UK. He has presented his research findings at major national and international conferences and was awarded Fellowship of the Academy of Pharmaceutical Sciences in 2017. Research from his group has led to more than 130 publications, which include research articles, review papers, journal editorials, book chapters, PhD thesis, published conference proceedings, and patent applications, as well as over 90 abstracts at various national and international conferences. Afzal is the founding associate editor of the Journal of Pharmaceutics and is on the editorial board of 4 other journals, including Nature Scientific Reports. Please welcome Professor Afzal Rahman Mohammed. Thank you.
Right, thank you for the kind introduction. I just want to mention that I'm more a Teams person, Microsoft Teams, so bear with me if there are any technical challenges using Zoom. I'm trying to find my way, and I'm sure we will get there in the end. Just bear with me, please. I hope you can see me and hear me.
can see you.
Right, right. Are you able to see my slide as well?
Yes.
Right. Shall I make a start?
You can start, please, on slideshow. Yeah.
Yes, because it's, I'm not a Zoom person, so, I'm not, and I can't see anything else on my screen but my presentation. If there are any technical issues, please somebody speak up and stop me. Also, I have a little video in my presentation. Let's hope it works. If it doesn't, then I'll skip that slide. Okay. So thank you very much.
Yes,
I
Prof,
want
you
to.
can click on the slideshow. At the bottom right.
Sorry, apologies.
At the bottom right, on the slideshow. Towards the volume, just before the volume. That's the slide. That's the icon for slideshow.
Oh, are you not? Do you not see?
Bottom right. Bottom right. Before
Right.
the volume, just that icon before the volume.
Before the volume. Which one is
right,
it?
Yes.
Right.
Or you can press F5.
Right. Okay. Is it working? Are you able to see my slide deck?
Yeah, I've seen your slides, but not on slideshow.
Oh, it's not on slideshow. It's slideshow at my end. So my apologies. So thank you for correcting me. Bear with me. I'm very familiar with.
Okay, it's also written at the top, slideshow.
Right. Bear with me.
You can continue.
No, I would very much prefer to have a slideshow rather than the PowerPoint mode.
Top, it's written there. It's clearly written out, slideshow on top.
Let me stop sharing first. Then perhaps. Oh God, I knew this was going to be a challenge. But nevertheless, I'm sure we'll find a solution. Any luck now? Do you see that as a slideshow?
Share your screen. Share your screen.
Oh, my screen's not shared. Right. Okay, let's start again. Can you see my slide deck?
Yes, you can go ahead, please.
And is it in a slideshow mode or is it just a PowerPoint mode?
Not yet. It's still in PowerPoint mode.
Right. Okay. I very much.
It's read. Yes, that's it. That's it. Perfect.
Yes, I did that before as well. Are you able to see my presentation in a slide as a presentation mode?
Not yet.
No? Right. My sincere apologies to the attendees. I am trying my best to make it work.
You can share from your system. You can click on share from Zoom.
Right.
You're no longer sharing your screen, Prof.
Bear with me. Sorry. Let's go back and start again.
Thank you.
Sorry, you said.
Can you see screen?
Yeah.
From share.
Yes, I've done that.
Okay.
Right. Let me see if I could.
Double click.
Is it working now?
Not yet. Let's continue, Prof. Let's go ahead.
Can you see my screen?
Perfect. Yes.
Yeah, you can see my screen.
Yes, please.
Right. Okay. I want to start by thanking the organizers for a very well organized presentation, a very well organized conference. The theme of my presentation this morning is patient-centered innovative drug delivery systems, and I'm going to focus on developing medicines for children. Duncan did a fabulous presentation. He captured his sort of research journey all the way from when he first started working with poorly soluble compounds to some of the more recent work around the application of AI. What I'm going to do is basically take a leaf from his presentation, but it won't be as expansive and elaborate as Duncan's. But what I want to do is use this opportunity to really showcase how the research in my group has evolved over the years, and what and how we arrived at the new dry particle coating technology. So my presentation will touch upon the pediatric medicine development needs with a clear focus on orally disintegrating tablets. And within that, I want to share my experience of what I started working on at the early stages of my career and how I transitioned into new areas of development and what was the driving force behind that, and how that sort of led to the development of new particle coating technology and where we are at with that. So that's the gist of my presentation this morning. When we look at pediatric medicines, it's a very interesting area, although we can capture that under the banner of pediatric medicines. But in effect, you've got at least 3 or 4 sub areas that you need to be aware of. So because even though pediatric as a broad area covers children, we know that the needs of children are different for different age groups. So the formulation requirements and the composition of the delivery system when it comes to, for example, 1 to 2 year olds would be very different when it comes to 16 to 12 year olds, because there are other factors that we need to take into account. Particularly, these different subsets have differences in terms of their physiology, in terms of the cognitive differences. So for example, if I were to translate that into practice, a single paracetamol dose, if you can look at the variability, right, it can range from as small as 30 milligrams to up to 1 gram for an adolescent. So this is where the complexity comes in. And this is where the pediatric formulation challenge becomes compounded. So what is an age-appropriate pediatric formulation? There are a number of criteria. For example, we need a dosage form which can deliver variable doses based on age, weight. The key criteria across the board, whether it's newborns or adolescents, is the excipient load, keeping the excipient load to a minimum. And that is actually one of the core areas of my research interest. And we'll touch upon that as we progress through the presentation. We need to make sure that the delivery system is able to deliver accurate doses. We need dose flexibility. We need to make sure that both the composition of the formulation and the delivery system is acceptable to the child. Aspects around avoiding medication error, that is another key consideration. So what we did within our research group was to focus our efforts on understanding orally disintegrating tablets. Now, what are these formulations? So these are typically solid dosage forms, look like a conventional immediate release tablets, but the key differentiator is that they dissolve rapidly in the oral cavity and therefore they can be swallowed as a liquid. I've got a little video here. Let's hope it works, just to demonstrate what an ODT looks like and how it works.
Yeah, please, Prof. I would like to let you know that your slide is not moving and we are not seeing the video you are playing. So we'll take a little interlude while we sort you out, please.
Okay. Do you want me to continue or park my presentation?
Just pause for a while.
Okay.
I've sent you an email, Prof. So, esteemed conferees, we have an interlude right now. I will sort out Prof. Kindly check your email, please.
Nothing in my email, I'm afraid.
We just sent it now. Please permit me to recognize some dignitaries in our midst. Professor Oluwole Familoni, former Deputy Vice Chancellor, Academic and Research. We appreciate you. Thank you for joining us. We want to appreciate Professor Asheku, the Dean, Faculty of Physical Sciences, University of Lagos. Thank you for joining us. We want to appreciate professors of the Faculty of Pharmacy, University of Lagos. We thank you for joining us on this call. And we also want to appreciate the speaker for tomorrow's, one of the speakers for tomorrow's event, Professor Agbakoba. Thank you for joining us, Prof. Thank you for joining us and staying with us up to this time. We'll reconnect soon. It's physical sciences. Thank you for this time. We connect. Please, while the going on, while it's going, kindly your question, you and ask President, you have questions, you and A. Professor Afzal Rahman Mohammed, we are ready now.
Okay, right. Let's start this again. Let's hope it works this time. That's the trouble, isn't it? With
We don't really use Zoom.
we don't
so-
use Zoom, right? So that's the thing. So if you go to, let's check. Hi, can I just check you're able to see my slide deck
Perfect.
and you're able to hear me as well?
Thank you, Prof. Yes, loud and clear.
Oh, my sincere apologies. Let's hope it works this time. I'm going to start from the start again then. Shall I do that?
Thank you, Prof.
Right. Okay. Thank you. Thank you. I want to start by thanking the organizers for inviting me to deliver this presentation. The presentation this afternoon will focus on patient-centered innovative drug delivery systems with a focus on developing medicines for children. The presentation this morning by Duncan Craig was a fabulous journey, research journey, starting from understanding the challenges of formulating poorly soluble drugs through to the most recent work he's doing on the application of AI in formulation and process development. My presentation, to some extent, mimics that similar format. I've taken a leaf from his book, but it's not as elaborate as Duncan's. But what I'm going to do is I'm going to talk about pediatric formulation development with a focus on orally disintegrating tablets. And then the key sort of pivotal moment in terms of how we've transitioned from asking the research questions around how this works, why it works, to what if. And that transition, that move to the what if mode was the basis for innovation in our research group. And we developed the dry particle coating technology. I'm going to talk about the journey around how it came into existence and what we've done with it and where we are with it now. And hopefully that should sort of summarize the work we've been doing with the last 7 to 10 years in terms of progressing the pediatric formulation platform. So when we look at pediatric formulation development, although it's a single sort of domain, single area of research, but in effect, in practice, there are multiple subsets within that, because these subsets are there due to differences in physiology between the different age groups in pediatrics, due to differences in cognitive abilities. So, for example, the type of formulation that you would want to create for drugs that are given mostly to, let's say, children up to 2 years old would be probably different to what you would give to an adolescent. So, for example, if I take paracetamol, something that we are very familiar with, the dose of paracetamol within the pediatric spectrum can vary from 30 milligrams to up to 1 gram. And this is based on age, based on weight. So that therefore helps us appreciate how the formulation challenge is very compounded within the pediatric group itself. So what is an age-appropriate pediatric formulation? What are the key considerations? So one of the primary considerations is the ability of the delivery system to deliver variable doses based on age or weight or whichever metric, whichever formula different parts of the world use. However, the key that cuts across all the different age groups is the excipient load. And that is something that I will focus in my presentation today. The formulation needs to deliver accurate dose. It needs to be safe and acceptable to children. Formulation acceptability is a huge area within pediatric formulation development. And to address these key requirements, the focus of our research was the formulation of orally disintegrating tablets. Now, these orally disintegrating tablets are solid dosage forms, look like a typical tablets, but the key differentiator is that they dissolve within the oral cavity and therefore turn into a liquid, and the liquid is what is swallowed. I've got a little video. Let's hope the video works, just to demonstrate how the ODT works. Let's hope the technology is on our side. It hasn't been. So that's a typical ODT, solid dosage form, but dissolves rapidly when it comes in contact with saliva. So the first phase of work, so to speak, typically in around 2007 to 2010, was to evaluate the role of material properties. My research group focused a lot on understanding the composition of ODTs and what are the material properties, and how could we matchmake between material properties and formulation of ODTs. Now, the key here in terms of the formulation method was freeze drying, because ODTs can be made using various different techniques. My interest at the start was to look at freeze drying as a method of manufacture. So we looked at the feasibility of incorporating amino acids, because in a typical freeze-dried ODT, you've got a scaffold made of polymer, and you need matrix supporting agents. In other words, these supporting agents are like nuts and bolts, ensuring the integrity of the polymeric scaffold. And we started investigating amino acids as these nuts and bolts, these matrix supporting agents to support the polymeric fabric. Why amino acids? Because these are naturally occurring compound, and they give us significant pharmaceutical advantage in that, from a charge perspective, you have zwitterionic amino acids, you've got positively charged, negatively charged amino acids, and these are very well characterized excipients. And therefore, the objective was to firstly evaluate the feasibility of using them as matrix supporting agents, and most importantly, to see if we can control the excipient burden. As I said, one of the key criteria is the excipient load when it comes to pediatric formulation, and the regulators are pretty stringent about this. They're looking at ways of reducing their various classes of excipients, and within each class, they want to make sure that the concentration, the excipient burden, is kept to the minimum. So we did some work around material sciences. We evaluated amino acids. We published fairly regularly in this space. We also looked at process development. Typically, as I said, at that time, the interest was around freeze-dried ODTs. And that led to a series of patent applications. Then, of course, as an academic, we always have a keen interest in translational outputs. We want to make sure that whatever we do within our laboratories is able to make a difference to people's lives around us. So I reached out to a number of different industry partners with the hope of exploiting these patents. But very soon I realized that even though there was an interest in pediatric formulation development, the need to use freeze drying as a technique, that put a significant number of industry partners off, because freeze drying as a scalable technique is not commonly available. And at that point, having taken the feedback from industry stakeholders, I transitioned from working on freeze-dried ODTs to directly compressed ODTs. One of the first couple of projects I was interested in when working on directly compressed ODTs, was to formulate ODTs with multiple APIs. So typically looking at fixed dose combinations. So you would have API 1 or API 2, and then you blend it with various excipients, characterize your powder blend, and compress them into an ODT. So that was one of the PhD projects that I had running in my group, looking at how we can increase the drug load and how we could deliver multiple APIs in a single tablet. It was quite an ambitious project. However, what happened was we wanted to make sure that when we deliver multiple APIs in an ODT, we have no choice but to keep the excipient load as low as possible. And that was needed for various reasons. Firstly, you can't sort of infinitely increase the size of the tablet. So typical ODT has to weigh around 500 milligrams. And if, for example, if you want to deliver 200 or 250 milligrams of the API, whether it's a single API or multiple APIs combined, then you only have a wiggle room between 200 to 250 milligrams for your excipient. So the hypothesis we had in that particular project was to actually keep the excipient load by careful deposition of excipients on drug particles, and therefore by doing that, we can not only keep the excipient load to a minimum, but at the same time, we'll be able to increase the amount of drug that we load in a given tablet. So that was our primary hypothesis that we wrote down in order to understand how we could deliver fixed dose combinations using ODTs. Of course, it was a great idea, but what we found quite early in the process was when you start blending API particles with excipients, you have significant challenges around the distribution, because we wanted to keep the excipient load to a minimum, and we saw pretty early that the ability to generate uniform blend with a small concentration of the excipient was proving to be very, very challenging. Either you had excipients forming layers in between drug particles, leading to streaking, or you had aggregates of excipients being distributed between drug particles, and that led to non-uniformity of the resultant powder blend. So we couldn't use either this or this powder blend for further downstream processing to make tablets. And we went back to the drawing board to understand what is it that is going on, and why is it that we're seeing this streaking? Why do we see this aggregate formation? We evaluated a range of different techniques, and the output was the same, irrespective of what blending technique we used. Whether we use gentle blenders, low shear blenders such as cube mixers or V blenders, we had the same issue. Or when we went down the route of high shear blending, the challenge was exactly the same. So we went back to the drawing board to try and understand what is the reason. And very soon we realized that the existing mechanisms of blending materials were based on the movement or solid movement of particles. In effect, what that meant was these particles rolling over each other. And this movement of particles was the key driver in terms of distributing the particles within a given powder bed. And what we realized was, for example, when we used a high shear homogenizer, that the environment that the particles experienced were varied depending on the location they were within that blender. So for example, in a high shear blender, you've got a static vessel, and inside you have a high-speed rotating baffle with blades. And the particles close to the blade experienced a different sort of forces compared to the particles that were at the periphery. So, for example, the particles at the periphery experienced high shear because of the high velocity associated with the particles at the edge of the baffles. However, on the other hand, when we looked at or what happens to the particles closer to the baffle is that they begin to aggregate. So the two main areas or the two challenges when we use high shear blenders is particle attrition or charge buildup. And as a result of that, because of the charge buildup, you see aggregate formation. And because of the particle attrition, you see new particle surfaces being formed, which can lead to agglomeration. So when we looked at other techniques, we arrived at the same finding, which was that the principal driver when it comes to blending was that there is movement of solid particles, and this is the primary force that allows for creating the uniform powder blend, which then led us to pose an ambitious research question. What if the powder bed is fluidized? Because every technique that we've evaluated and things that we've looked at in literature, the fundamental mechanism was based on the solid movement of the particles. So the question we asked ourselves was, what can we expect if the powder bed is actually fluidized? And when you fluidize the particles, can you actually create a uniform mixing zone? So you can see how the research project, where the primary research hypothesis we had was to keep the excipient load to a minimal in order to deliver multiple drugs in an ODT, how that is now evolving into a more process-driven project, where the primary question has now shifted from how we can reduce the excipient load to what would happen if the powder blend, if the powder, including the APIs and the excipients, was fluidized. So we actually conceptualized a piece of kit where we had a high-speed rotating drum with a hollow shaft, and hollow shaft comprising of these little holes. And through the hollow shaft, we were able to introduce air. Most of the work we've done subsequently was with nitrogen for obvious reason, because nitrogen provides an inert environment. And this hollow drum was closed from both sides, and this drum would move at high speed and the hollow shaft would be static. And you can introduce air or nitrogen through this hollow shaft. And when this nitrogen enters into the drum, it leaves these little outlets, these apertures, and therefore hits the powder that is in the rotating drum. So that was a little cartoon that we put together, and we conceptualized and we translated that into what I call as our first generation of quota, where we've taken a plastic casing. We had an old homogenizer head that had been discarded because the other parts of the homogenizer were not working. We worked very closely with the technical team. We then assembled this piece of kit. And what we were able to do was create the processing chamber with the opportunity here for a hollow shaft to introduce air. And this motor would control the rotation of this chamber. So we had this first prototype where we translated our sort of theoretical dry coat or fluidized powder bed into practice. And what did we find? Very quickly, we found that when we started to blend materials, and please, this is just a dye that we used because majority of the excipients that we see in the pharmaceutical world, as you know, are white. So we just wanted to ensure that what we had in terms of a process was able to generate uniform blend. So we used a dye and we used microcrystalline cellulose as a carrier, as a model carrier. We added the two together and the drum was rotated at high speed. And this is what we found as the resultant product. So what not only you can see that the dye is uniformly distributed, although you can't see here very clearly, but the size of the particles between the resultant material and the starting material remained unchanged. So for us, that was an exciting outcome. And it was exciting to see how the hypothesis we had literally drafted on a piece of paper and the bits of equipment or the bits of non-functional kit that we had, how we've assembled them together to generate a new process or to develop a new process. So this was the first piece of data that my group generated. This was then followed by what I call as the eureka moment, because when we finished the work with a colored dye, the student then started to use more pharmaceutically relevant materials. So she went away and started to use or started to coat, for instance, the drug candidates or drug molecules, drug particles with various different concentrations of the polymer. And she came to see me and said, "Oh, I'm not sure what's going on here, right? We changed the concentration, the release profile is changing. So at a low concentration, we see a higher release. And as we begin to increase the concentration of the polymer, we start to see a change in the release profile." And I said, actually, this is a fantastic outcome, because what this is showing us is without changing the material composition, just by changing the concentration. So the starting material was the same. In other words, the drug particles and the polymer were the same without changing the polymer type. Just by altering the concentration and processing it through the dry particle coater, we are able to modulate the release profile. And I said, this is an exciting piece of work. And following that, pretty much there was no looking back, really. And the next step for us was to really understand what is going on, how do the particles behave when they process through this dry particle coater, what is the mechanism of this dry particle coating. So we termed it isothermal dry particle coater because the most interesting thing in terms of from a process point of view is that this process operates at ambient temperature. So the entire process of coating takes place between 22 to 24 degrees centigrade. So hence the word isothermal. And we don't need to put any solvents, hence dry particle coating. And therefore, we coined the term isothermal dry particle coater. And we use the word thin layer fluidization because the air jet that is introduced into the high-speed rotating drum creates that air curtain which fluidizes the particles. And this process of fluidization allows the particles to be in a fluid state and increases the probability of the small particles interacting with the large particles. And given the fundamentals of physics, whereby the small particles have larger surface area and are in a high energy state, they land on large particles which have relatively lower energy, and that is how they lower the energy state. And that is what gives rise to the coated particles. How does this happen? What I've tried to do here is try to oversimplify this. So first step, when you introduce nitrogen or air into the rotating chamber, what happens is this creates an air curtain or a nitrogen curtain, and this nitrogen curtain acts like a scraper. And this scraper then fluidizes the particles. So everything is in a fluid state. Your excipients, drug particles, everything is in a fluidized state. And that leads to deagglomeration. So the first challenge associated with agglomeration, that is sort of addressed here. Following deagglomeration, what we see is the high-speed rotation of the drum allows for dispersion of these particles. So these particles which are still in the fluidized state, the high-speed rotating drum allows them to move in different areas of the powder bed. And that sort of gives rise to the dispersion of particles, whereby the probability of different materials coming into contact, particularly the particles where you have differences in particle size, where you've got fine particles and large coarse particles, you have the greater probability of interaction. And then as a result of that increased probability, what you see is the adsorption of fine particles onto coarse particles. And this adsorption leads to the process of dry coated particles. Now, this, if I was to sort of summarize it in one slide, the process of deagglomeration is followed by dispersion of particles and then adsorption, which then gives rise to the dry coated particles. Now, this dry coating can be discrete, where you've got areas of large particles exposed where you don't have any small particles, and that can easily be controlled by increasing the concentration of these small particles, and therefore you will end up with a monolayer coverage. So by controlling the concentration, you can ease of the very fine particles. You can either have discrete coating, or you can have a more uniform monolayer coating by increasing the concentration. Is there any evidence for this? Yes, of course. What we've done is we used microcrystalline cellulose and we used rhodamine as a dye, and we processed it in the dry coater. And rhodamine was used because rhodamine is a good fluorescent material. When we observed these dry coated particles under a confocal microscope, what we could see here is that all the particles are fully coated with rhodamine, so you don't see any free rhodamine in the field of view. And if you zoom in and look at individual particles, what confocal allows you to do is identify a single particle from within the field of view and basically slice these particles. And these are the two slices that you can see here. So you can create a slice, and what you see here is there is a dark region here, which is your microcrystalline cellulose, because microcrystalline cellulose doesn't fluoresce, and you have a thin layer, a thin ring of rhodamine which fluoresces, and that is also evident in this slice as well. So this confirms that the rhodamine was coated into microcrystalline cellulose, and that you have a very uniform coating layer on the surface of the microcrystalline cellulose particles. How did we study this further, and did we actually did we achieve what we set out to achieve? And I just want to remind you that one of the primary objectives in that particular project, where we were looking at fixed dose combination, where we wanted to minimize the excipient load, was to see how we can reduce the amount of excipient. Did we achieve that? I'll leave that for you to conclude, because large particles coated with fine particles. So here we've got 0.7% of fine particles, and when we increase the concentration of the fine particles, you can see greater deposition on the coarse particles. So here, this proves that we can actually control the deposition of very fine particles onto coarse particles, and that each of these individual particles you can see that are coated, they're fairly deagglomerated, although you do see pockets where you've got small aggregates, but in more broad sense, they're fairly well deagglomerated, and there's nothing in the field of view. All the fine particles are coated on the surface of the larger particles. We went on to continue this work, and here's another example where this is the uncoated drug particles, and we can demonstrate here that by increasing the concentration of the coating material to higher concentration, you can achieve full coverage. So these are two further examples where uncoated particles, when processed through dry coating and controlled excipient load, you can create a full monolayer coverage of coating material. So the prototype works, and therefore, and there's plenty of evidence. I hope I've convinced you of the dry coating. The question is, what's next? So where do we take this prototype that we put together? What have we done with it? We were able to then translate the principles of this coating process into a GMP-ready benchtop system where you can handle anywhere between half a gram of a material to up to 20 grams. Not only have we able to translate that into a GMP-ready kit, we've also demonstrated the scalability of this process. So we've looked at creating different concentrations of different blends, and not only were we able to demonstrate the reproducibility between a benchtop system and a pilot system where we can scale up the process to up to 2 kilograms. The most interesting outcome is that these formulations that we've developed were stable for at least 2 years, and those stability studies are still ongoing. And this is a pilot scale version of the prototype that we have. And this, again, is GMP ready. Now, what is interesting is the origin, the genesis of this particular dry particle technology was purely to modulate the excipient load in a pediatric formulation. But over the past 5 to 7 years, we've realized that this has a broader application. In fact, this is a platform technology. It can be used to formulate inhaled dry powders, whereby you need, again, deagglomeration of fine particles. You're constrained by the particle size of the drug particles when it comes to inhaled delivery. So this particular technology has applications in the formulation of dry powder inhalers. It can be used for taste masking. So where you've got a bitter tasting drug, you can layer it with fine particles of polymers that are neutral tasting. As I mentioned in my presentation, you can have either discrete or monolayer coverage. So if you had monolayer coverage, you're able to basically mask the taste of the bitter drug particles, and therefore overcome the taste challenges, particularly within the pediatric formulation development arena. Given this process operates at ambient temperature, this process lends itself to the formulation of very heat-sensitive drug candidates, such as biologicals. And there's also data that we've generated around improving the dissolution, whereby we take a two-pronged approach. We are able to reduce the particle size of the drugs. And as Duncan mentioned in his presentation, it is something that's done pretty routinely. But the challenge with reducing particle size is that these particles begin to agglomerate because of the high surface areas. But what we are able to do is take drugs with poor solubility, reduce the particle size, and then coat these fine particles of the drug onto polymers that are hydrophilic, larger particles of polymers that are hydrophilic. And basically, it's a double whammy. You have a dual advantage. You are exploiting the particle size principles of particle size reduction to improve solubility, but the hydrophilic nature of the larger particles onto which you're coating the drug particles also allows or improves the wettability of the polysoluble drug. So you're able to take a two-pronged approach and improve the dissolution properties of polysoluble drugs. So in summary, IDPC, isothermal dry particle coating technology that was developed as part of a PhD project, has applications in a number of different areas, allows faster development of medicines to market because this process, you can work with very small quantities of material and the process is scalable. It can go all the way, you can scale up the process to a pilot scale very easily, up to 2 kilograms. And this particular technology is actually being commercialized through a spin-out company, Aston Particle Technologies, and the companies have already developed a larger sort of a batch size, and is also working on developing a semi-continuous process as well. So that's happening as we speak. It's an it's a sustainable and environmental friendly technology because you don't need to use any solvents and everything happens at room temperature. This particular technology lends itself to design of experiments. So the regulators across the globe are now more keen for formulation development to go down the route of design of experiments. This technology lends itself because it has very well-defined process parameters. So the variables include the speed of rotation, the duration of processing, and the flow rate of air or nitrogen into the process. So basically 3 process variables. It can be used as a differentiated technology for new drug candidates, and it can also be applied to increase the lifespan of existing generic compounds or existing drugs that are coming off patent in the near future. So hopefully that's sort of given you a flavor of the work within our research group. And I want to conclude my presentation by thanking all the collaborators, the funders, including the government funding, research councils, industry, Innovate UK, and of course the team members who've contributed to research in my group over the last couple of decades. Thank you. I'm happy to accept any questions.
Wonderful presentation. If we are still on translational research, you all will agree with me that we ultimately handled the topic very well. Specifically, pediatric medications with focus on orally disintegrating tablets. They achieved benchmarking, dissolution enhancement, stability and scale up, ultimately to enhance drug acceptability and adherence. This is indeed a cutting-edge, innovative research. Another round of applause for Prof.
Thank you.
We will take 2 or 3 questions. The first one, Prof, it says, thank you, Professor Afzal. Can the instrument developed in your lab confirm the taste masking of formulation in pediatrics? That is, assuming you are able to create a monolayer of neural testing material on the formulation. That's question 1.
Do you mind just repeating? I had the monolayer and beta testing drug. Do you mind just repeating? Please.
It's in the Q&A.
Okay.
I can repeat it, sir.
Yeah.
Prof. Afzal, can the instrument developed in your laboratory confirm the test masking of formulations in pediatrics? That is, assuming you are able to create a monolayer of neural lasting material on the formulation.
Yeah. No, thank you.
Neutral taste material on the formulation.
Yes, no, thank you. It's a very good question, very relevant. Yes, we've done a lot of work around taste masking. We've looked at a range, quoting a range of different types of polymers, um, looking at the impact of charge of the polymer and the concentration of the polymer, and making sure we generate uniform monolayers. We currently assess the taste masking efficiency through indirect assays. We look at the drug release profile. So what we do is we evaluate the drug dissolution using the pharmacopoeial methods. And what we're looking for is a slight reduction in the drug release in the first 2 or 3 minutes, because that is the duration when the drug particles are in contact within the oral cavity, and then followed by an increase in release to match the dissolution profile of other formulations. So that's one way we're assessing. We've also got we've developed a small volume drug release method as well, and there's a third piece of work which is still, I'd say, in the exploratory phase. We've actually published an article looking at isolating bovine taste buds from bovine tongues. We published a paper where we've characterized the cell culture side of things, and what we want to be able to do in the near future is to use that particular cell line to differentiate the taste response. But as it stands, yes, we've evaluated the taste masking efficiency, and we use indirect methods to assess that, including drug dissolution, as well as some small volume drug release methods as well. I hope that answers your question. I hope that is what you were referring to in the question.
Yes, Prof. Thank you so much. Another round of applause for Professor Mohammed. That brings us to the end of the Q&A. It's now time to present him his plaque. Presentation of award, it will be done by Dr. Uloma Ubani Ukoma. Presentation of the award to Professor Rahman Mohammed.
Thank you.
Professor Afzal, for that beautiful presentation. On behalf of the University of Lagos Faculty of Pharmacy, I am honored to present this award to you, Professor Afzal Rahman Mohammed, as the plenary speaker in this fourth Faculty of Pharmacy Virtual Scientific Conference. Thank you very much, sir, for the beautiful presentation. We'll make sure this gets to you the next 1 or 2 months. Thank you.
Thank you. I'm really honored. Thank you very much for that. And I sincerely apologize for the technical challenges we faced at the start of the presentation. I did start my presentation my presentation with a caveat that I'm more of a Microsoft Teams person, because I'm very familiar with how to use different sort of tools and buttons in the Microsoft Teams. So Zoom is very rare. So my sincere apologies for that. But thank you very much for the invitation and this wonderful conference.
Another round of applause for that scintillating presentation. We have learned a lot from your presentation. Before we go to the next second plenary speaker, we are going to invite Joyce Ogabi to pitch on PBR Life Sciences for 10 minutes. We are making you a co-host now, Joyce Ogabi, so you can share your slide.
Okay, thank you very much.
Share your slide and turn on the video. Thank you. We are not seeing your slide yet.
Yes, you should be seeing it now.
Thank you.
Mm. All right. Good afternoon, everyone. I'm really happy to be here. My name is Joyce Sogabi, and I'm an associate and of an analyst and insight associate at PBR Life Sciences. I'll be sharing how we're unlocking Africa's real world healthcare insights through our new platform, PBR Research Data Lab. Our focus is bridging Africa's health data gap with clean, curated data sets that enable transformative research and decisions. PBR Life Sciences is an AI-powered contract research organization with operations in the UK, Nigeria, Ghana, and Kenya. We combine advanced analytics with local expertise to deliver the real-world evidence that global pharma and academia need. In a nutshell, we connect cutting-edge data science with on-the-ground African realities. What is the problem we're solving? Africa's healthcare data ecosystem faces several barriers: poor digitization, inconsistent quality, and limited inclusivity, especially in rural areas or lower levels of care. This means that Africa is largely absent from global data sets used for AI modeling and medical research. Local research teams also struggle to access structured, usable real-world data. This gap is what we are set out to close. Our vision is simple: to bridge Africa's health data gap and to power evidence-based decisions that transform care, policy, and outcomes. For the first time, researchers can seamlessly access pharmacy, claims, and clinical data sets in one place. These data sets are clean, curated, and they are analysis ready. Now, we'll dive a little bit into the Research Data Lab. The Research Data Lab it's not just a data repository, it's a full technical environment where researchers can work end to end. On the infrastructure side, from this, you can see it's based on Microsoft Fabric with OneLake and Lakehouse storage, giving secure and centralized access. Pipelines and data flows automate the cleaning and transformation of raw data, while enterprise-grade governance ensures NDPR compliance and data protection. For analytics, users can query datasets using SQL or PySpark, run advanced models with Python, and leverage AI copilots for exploratory analysis. There's still more this platform can do. It contains visualization tools like Power BI, which makes it easy to turn findings into publication-ready outputs. For academics, this platform is research-ready. The visual on the right shows some of the inbuilt features of the platform. You can see the SQL and PySpark features, as well as a sample query and results when run. The three red arrows are what indicate what I'm referring to. So I'm going to be going into our data sets on the platform that you'll really be interacting with. Our data sets, they span the full healthcare value chain. So it gives researchers an end-to-end view that is unprecedented in Africa. Versus, for example, is our retail platform. It contains over 1,500 outlets across Nigeria and Ghana with historical transaction data dating back to 2021. This provides a unique lens into medicine utilization, patient adherence, and affordability at the retail pharmacy level, which is the first point of contact with the health system for most patients. Our Invisio platform provides hospital and HMO claims and includes data from over 4,000 hospitals classified by level of care. It's classified into primary, secondary, and tertiary levels of care. We also capture about 600,000 anonymized patient records covering demographics, diagnosis, and outcomes. This allows researchers to study disease burden, cost of care, treatment patterns across different settings. We have standardized more than 13,000 SKUs, 5,000 molecules, and 600 diagnostic tests using WHO, ATC, and ICD-10 disease classifications. This ensures that our data is globally comparable while still reflecting the local realities. It supports everything from pharmacoepidemiology and health economics to outcomes research. Together, this breadth and depth gives us unprecedented visibility into healthcare patterns in Nigeria and Ghana, making it possible to study not just isolated data points, but to understand how the entire health system functions at different stages, including import, distribution, retail pharmacy, and the hospital. What's in it for researchers? What do researchers stand to gain from this platform? Using the Research Data Lab, studies can be published up to 40% faster using pre-created data sets and reusable workflows. The cost of analytics is reduced, and studies are more likely to be published in high-impact journals because of the novelty and breadth of African-centric data used for the research. We provide teaching data sets and training modules to help students and faculty grow real-world data expertise. Researchers can collaborate securely across borders in an audit-logged environment. We also help teaching hospitals set up compliant data hubs so that routine care data can be turned into the identified research data. That's not all. One of the unique benefits is the ability to build patient cohorts. It means you can group patients by age, by the gender, by their diagnosis or treatment history, and then study by their outcomes, adherence, and even cost of care. This opens the door to comparative effectiveness studies and better clinical trial design. Let me ask a quick question. How many of you have conducted a study involving about 2,000 participants? And what challenges did you face doing this? To demonstrate the power of the platform, let's look at sickle cell disorders in Nigeria based on data from 2024. Now, this study was undertaken using just data from the Research Data Lab. Our analysis covered over 3,000 patients, showing an average age of 22 years. Vaso-occlusive crisis emerged as the leading complication, with HBSS patients experiencing the highest encounters. Most visits occurred at secondary facilities, and the majority were outpatient-based. We also identified top prescribed drugs and investigations, highlighting where resources are concentrated and where interventions could reduce costs and improve care. This kind of granular population-level view is only possible through real-world data at scale. You can view and download the white paper at no cost by scanning this QR code. Give us some seconds to scan it if you want to go ahead and do that. In summary, the Research Data Lab is the first African-focused hub that unifies pharmacy, hospital, lab, and claims data into one secure and scalable ecosystem. It's comprehensive, integrated, and built for the future of health research on the continent. We invite you to be early adopters of the Research Data Lab, whether as academics or as collaborators. Scan the QR code to sign up for trial access or reach out to our team to explore partnerships. I'll give us some time to scan the QR code. Do this. You can also explore the various monthly subscription packages based on your research needs. We have the details on the screen. You can take a look if you see the one that's relevant to your research, the one that aligns well with your research needs. We'll be happy to partner with you. Thank you very much for your attention. I'll be happy to take a few questions.
Thank you so much, Joyce Ogabi, for that 10-minute speech on behalf of PBR Life Sciences, talking about Research Data Lab. In addition to the QR code, you can please drop the link on the chat box so that people can just click and continue with you. Do we have any question, please, for her? Just one question. No questions. Thank you so much for that. Now we come to the second plenary speaker for today's event. It's titled Translational Natural Products into Therapeutic Innovation, Advancing Phytomedicine from Bench to Bedside. It will be taken by Professor Amala Sumyanath. Before the presentation, we call on Dr. Joseph Oshogaide to read her citation while she turns her video on. Thank you. Good afternoon. Good afternoon, conference participants. This is a citation for Dr. Amala Sumyanath, a professor in the Neurology Department, Oregon Health and Science University, Portland, Oregon, the US. She received her pharmacy degree and a PhD from the University of London, UK. Dr. Sumyanath Raman began her academic career as lecturer in the Department of Pharmacy of the King's College London. She taught a lot of pharmacognosy courses and helped modernize the pharmacognosy curriculum, including transition from the 3-year B.Pharm program to a 4-year M.Pharm course. At King College London and now at the Oregon Health and Science University, her research program has investigated traditional herbal medicines, exploring the validity and scientific basis of reputed biological activities. The goals are to support evidence-based phytotherapy and to identify natural product leads for conventional drug development. Dear participants, join me and welcome Professor Amala Sumyanath.
Hey, thank you. Thank you very much. Thank you, Professor Oshogaide, for the kind introduction. I also want to thank Professor Sofidia for the invitation to present here. As a pharmacist myself, I'm really delighted to be able to share my research and be in the presence of other pharmaceutical scientists from other parts of the world. So let me begin by sharing my presentation. I hope this is. Are you seeing my slides?
Yes.
Thank you so much. Okay, so I believe I'm ready to share my presentation now. Let me make the. Okay, thank you. Oops, are you still seeing them? No. Okay, you're seeing them, but I'm not.
You can go ahead, Prof. We are seeing your slides.
Okay, on my side, I'm not seeing them so well. So can I just start again? Let me stop share and start again. Okay. Okay, so you saw that the title of my talk is Translating Natural Products to Therapeutic Innovations. I'm here, greetings from Portland, Oregon, USA, where we've been working on some botanicals, as you will see. Now, I'll give you the outline of my presentation first. First of all, I would like to tell you about the Benfra Botanical Dietary Supplements Research Center, which is something that we have at my university, and then talk about the approaches that we've taken to researching traditional botanicals. I'm going to use the word botanicals because this is how we refer to them in the United States. But of course, what I'm talking about is herbals or phytomedicines. And then I will illustrate my points with describing some translational studies we've been doing on 2 neurologically active botanicals. And I would like to state at the outset that this is definitely not my work alone. I've been blessed to have some really excellent collaborators, both at my university and at other organizations who've contributed to this work. And this is truly a multidisciplinary effort. We have people ranging from neurologists, neuroscientists to analytical chemists. So I'm currently the director of something called the Benfra BDSRC. This is a Botanical Dietary Supplements Research Center, which is funded by the National Institutes of Health here in the USA. And this term Benfra is an acronym for Botanicals Enhancing Neurological and Functional Resilience in Aging. What are we interested in? And let me just confirm that you're still able to see my slides okay. We are studying changes in cognition, sleep, and mood, which we know, as we know, can be changed as we get older. And very often the quality of cognition and sleep and so on decreases as we get older. And what we're really looking at is whether botanicals can provide resilience to these changes that occur as we age. So as well as a normal decline in these processes, I want to emphasize, of course, that sometimes the decline can be made more rapid by the presence of some kind of pathology, some kind of disease. And we're all very familiar with the fact that Alzheimer's disease is one of the commonest sources of dementia, loss of cognitive function. And of course, the prevalence is increasing as the proportion of aged population in the world is also increasing. So which of the botanicals we're studying? Well, we're studying 2 specific botanicals. Both of these are very popular in the United States, where I'm currently from. But they're both derived from the Indian Ayurvedic tradition. So one of them is Centella asiatica, which is sold as the dietary supplement Gotu-Kola. And the second one is this herb, which is sold as ashwagandha, the Latin name being Withania somnifera. Why did we choose these herbs? We chose them because both of them in the Ayurvedic tradition are known as rasayana or rejuvenating herbs, potentially offering resilience to age-related challenges. And generally, when people take these as supplements, they use Gotu-Kola for memory support, whereas ashwagandha is used for stress and insomnia, but also for memory improvement. This is just a range of products that's available on the shelves. It ranges anything from just the powdered herb to make tea bags where you can make a tea, to products containing capsules, which are either just the dried herb or the extracts of the herb. So a lot of variability. And the same for ashwagandha. There are many, many products out there. This is just a small selection of them, and anything from the powdered root itself to various types of extract. And you'll see that what a patient is receiving or a person is receiving when they're taking these can range anything from the equivalent of 200 milligrams of the herb up to 1,000 milligrams of the herb. So there's a tremendous amount of variability. And so we really want to try and understand what is the best way to take these herbs, what are the types of, what are the products that actually work. So I want to mention that in the United States, there are 2. One of the commonest ways that you can get a botanical product is as a dietary supplement. And these are governed by a law known as the DSHEA, Dietary Supplement Health and Education Act. The main thing about this law is that it classifies dietary supplements neither as foods nor medicines, and it has certain rules which says certain allowances which says that you don't really need to have proof of efficacy before you market this product. And because of this, there are no standardized preparations, as you saw. But then there's also some limitations, which is that you cannot make any therapeutic claims on your label. And you also have to state that the FDA has not evaluated any claims that you do make. But on the other hand, if you want to, you can actually develop something called a botanical drug. There is a pathway. And in this case, you need to have a similar approval process to conventional drugs. And I'll come back to that point later. So how can we make sure that we have good evidence-based use of these botanical products? Well, if you look in the literature, you'll find that for many of the botanicals that people use medicinally and traditionally, there's a lot of in vitro and in vivo studies that have been done for these botanicals. However, we do need to see what the human relevance is, because as pharmacists and people in the pharmacy field, you know that what works in vitro and in vivo does not necessarily work in humans. And then if you go searching for clinical trials, you'll find that they're really limited or non-existent for most botanicals. And this is an area that we're trying to make a bit of a dent in and try and get more of these clinical trials going. The problem is also that whatever clinical trials are available, very often they lack scientific rigor for various reasons, and they're also tend to be very small scale. Another big problem in this whole field of natural products research is that people who do the studies and in the publications, you often find that there's a very poor description of the products used. As I've just shown you, for a given herb, you can have a multiplicity of products. So it's really important to give a good description of what product you've used, so that if you want to look at the generalizability of that data or know how it might relate to a different product, you will have a better handle on whether it can be compared. And as I mentioned here, the products vary between studies. So our goal at Benfra is to perform rigorous foundational research leading to well-designed clinical trials on well-characterized products. I've already mentioned that you can actually develop a drug as a botanical drug, but then you have to follow a similar approval process as you would to conventional drugs. And as you know, as pharmacists, this is the process that we usually follow. When we have a discovery or a lead, we put this lead through translational research, through in vitro and in vivo tests. We do some biomarker studies leading to clinical trials, comparing your material to placebo or other therapies. And then if everything goes well, this ends up in clinical practice. And for this, you need well-defined therapeutic targets, a well-defined study drug, and you also have to have good pharmacokinetic and pharmacodynamic data. So how can this be applied to botanicals? Well, of course, the first thing is to know that botanicals and conventional medicines are very different in many ways. They're both pharmacologically active, but whereas conventional medicine consists of a single chemical entity, usually you can have mixtures, but for the most part, it's a single chemical entity. There's a single active compound. You can make manufacturing processes which make it very reproducible. The active is well known. And if you're going to do these ADME studies, absorption, distribution, metabolism, excretion, you only have to worry about that one compound. And we usually have a good idea of its mode of action. By contrast, when you're dealing with phytomedicines or natural products, these are mixtures of chemicals, and there could be more than one active compound there. And not only are these mixtures, that mixture is not uniform or standard. You can have a very variable chemical profile, which is affected by genetic, geographical, cultivation, and processing factors. So you don't always end up with the same thing. And you don't always know what all the active compounds are, and you really have to study this as a mixture. So what I hope to do is demonstrate how we've tried to address this issue in our work. Now, the National Institutes of Health has come up with a roadmap for how to work your way towards doing efficacy trials of these natural products, bearing in mind these different challenges that you have with these natural products. And they say that, of course, everything should be based on historical use and fundamental preclinical knowledge. But before you start doing your efficacy studies, it's important to do a whole lot of groundwork. And what this really boils down to is having a mixture of a knowledge of the biological effects of your plant material and what the active compounds are. Because when you know what the active compounds are, you can then make an optimized dose and formulation. You can ensure you have a product of the best quality, making sure that the active compounds are there. You can do pharmacokinetic studies to make sure that they're bioavailable. And then on the biological side, you can also make sure that you're selecting the right population and that you're looking for the right efficacy markers in that population. So again, I hope to demonstrate this in the work that we've been doing. So at the Benfra Center, we've envisioned this roadmap as this pipeline where it's important, of course, to start by using an authentic product and optimize it for the best activity, which involves, and you'll notice these arrows are not one-sided, they go back and forth. We need to know what the active compounds are, and also we want to be able to demonstrate a functional effect in vivo and go back and forth between these different aspects so that we have a good understanding of the chemistry and the biology and how they are interconnected. And also identify translationally relevant biomarkers. And what do I mean by that? What I mean is that if you know the mechanism by which your botanical is achieving an effect in an in vivo system, can you identify certain markers which you are also able to measure in a human being when you give them the same botanical product? And that's what I mean by a relevant biomarker, a biomarker of target engagement by your botanical. Now, in terms of the two botanicals that we've been working with, we have come a long way with Gotukola or Centella asiatica, and the rest of my talk is going to be describing that work. And we've now started to look also at ashwagandha. We're a little bit earlier in the pipeline with that, although there is a tremendous amount of literature on ashwagandha in the public domain. Okay, so let's start by talking about Centella asiatica. Mostly we've been working with a water extract of this herb. This has been optimized based on previous studies which suggested that using water as your extraction method brings out the best compounds for cognitive improvement. And this has been done before where other researchers compared different extracts. So we've used this water extract and we've done a combination of in vitro studies in neuroblastoma cells, mouse primary neurons, and then also studied it in vivo, and then studied a lot about the chemistry of this herb and what might be the active compounds, and done safety studies of this herbal extract in animals. And we're now currently doing a clinical trial. I won't be saying very much about the in vitro studies, actually I will. I'll say a little bit about the in vitro studies, but show you how we went through this translational process. So first, a little bit about our disease target. We are thinking of developing Centella we're talking about translational work to develop an innovative way of treating Alzheimer's disease. So just to remind everyone that in Alzheimer's disease, one of the main pathological features that one sees if one does a biopsy of the brain or does a post-mortem analysis is that there are high levels of this protein called beta amyloid, which is abnormally deposited, as well as phosphorylated tau protein. So these protein deposits are one of the features of Alzheimer's disease. But at a cellular level, you also see a very high oxidative stress and also mitochondrial dysfunction, all of which lead to neurodegeneration and then the symptoms of Alzheimer's disease. So one of the first tests we did was just to see what effect Centella had in protecting nerve cells from the toxicity of beta amyloid, this protein. So we used two types of cells. And in this experiment, basically the first bar represents just a control condition where we're just growing the cells. The second bar represents where we've added Centella extract to the cells and we're growing it. And the third bar represents the presence of beta amyloid. And you'll see this measures viability. You'll see immediately there's a decrease in viability of these cells in the presence of this toxic protein. However, if we culture the cells also in the presence of CAW as well as beta amyloid, the CAW is able to offer protection to these cells from the beta amyloid toxicity. So we were very excited by this result, and then we went on to do some in vivo studies, and there are different models that we used. There are two particular models of Alzheimer's disease that we use in our lab. We've been focusing more on the second one of late, which is the 5XFAD model. These are transgenic mice which have been engineered in such a way that they develop these beta amyloid plaques in the brain, and this is accompanied by various cognitive impairments in these mice. We've also been studying centella just in aged mice based on its traditional use, where it's not used specifically for Alzheimer's disease, but just as a rejuvenating herb. So this is the first experiment that I want to share with you. In this study, we took control mice, we took 5XFAD mice, which is the Alzheimer's model, and wild type mice. Wild type just means that they're normal mice, which don't have the transgene that causes the amyloid deposits. And they either received ordinary food and water, or they received ordinary food, but in the drinking water, we put different doses of this Centella asiatica extract, the CAW. They received this in the drinking water for 5 weeks, and from week 2 onwards, they were subjected to a cognitive test. And at the end of the 5 weeks, we were able to take their brain and blood and then do some analyses to see what mechanisms we could see for our extract. So here's the cognitive test that we applied. In this case, the mouse is placed in a chamber which has a wire mesh, and a shock is applied as a noxious stimulus. You take the mouse out and return it to the chamber at 24 hours. And if it remembers the shock that it previously received in this chamber, it will freeze. And what we can do is measure the amount of time it spends freezing. So what we found was that as we increased the dose of centella in the extract, the mouse froze for a longer period of time, which means that they remembered the freezing, the shock, better when they'd had a higher dose of this centella extract. And we basically found there was a significant dose effect. We found that the 5XFAD mice had a worse memory than the wild type mice. And there wasn't really a gender difference, but the most important thing was this demonstration that administration of centella could improve the memory of the shock in these mice. And the mechanisms that we found by analyzing the brain tissue was that there was an increase in gene expression for synaptic genes as well as antioxidant response genes, so the ability to respond to oxidative stress. Another study that we did was in just simply aged mice, so just mice of 20 months of age. And these were either received ordinary drinking water, or they had the CAW in their drinking water, and a similar paradigm of 5 weeks of treatment. And this is another type of cognitive test that we did, known as the object location memory test. In this test, you put a mouse in a chamber with 2 objects, and you take the mouse out, and meanwhile you move the location of one of the objects, and you put the mouse back in there, and then you take the mouse out, and then you put it back in after 24 hours, and you've moved one of the objects again. What does this test do? Well, mice are inherently curious. So if they remember the location of the objects, they should spend more time with the object that's in the new location because it's more interesting. And what did we find? Well, okay, so this was done in male and female mice, and they were either treated or untreated, treated with CAW or just control mice. So here, if we look at the female mice, the black bar represents the amount of interest in the new location. The white bar is the old location. So in this case, indeed, female untreated mice at 2 hours do show an increased interest in the new location. But if you have treated them with CAW, the relative interest increases significantly. The male mice did not show a significant difference in interest between the 2 locations if they were not treated. But as soon as for the mice that were treated with CAW, they did show an enhanced interest in the new location, showing an improved memory. At 24 hours, neither the female nor the male mice showed a preference for the new location, unless they had been treated with CAW, in which case they showed a very distinct preference, again indicating as the sign of an effect on memory. So this was exciting data. And again, looking at the mechanisms by which this was happening, what we found was in the brains of these treated mice, there was an increased expression of mitochondrial electron transport genes. So these are the genes which are responsible for the electron transport chain, which generates ATP. So it improved mitochondrial function in the brain and also increased antioxidant response, as I mentioned earlier. There's a transcription factor known as NERV2, which really controls the ability of cells to respond to oxidative stress. So, and then also we found this increase in synaptic genes as well. So in summary, what we believe are the mechanisms by which Centella works are an increased in antioxidant response, increased in mitochondrial activity, and also synaptic health. So what does this mean for Alzheimer's disease? Well, if you look at conventional drug research right now, what are the main areas of focus by pharmaceutical companies? They're really looking at ways of targeting this protein deposition. But it looks like what Centella does is to actually look at the neurodegeneration pathway and is actually able to offer some relief to this oxidative stress and mitochondrial dysfunction. So it has a unique mechanism of action, different from the drugs that are currently used. There's a whole other set of drugs that simply improve neurotransmission. So we're excited that CAW has this novel mechanism of action. And the interesting thing is that things like oxidative stress and mitochondrial dysfunction are also involved in non-pathological aging. Which is why it also works in the wild type animals and why it's helpful as a Rasaiyana herb. Now, what about active compounds? Well, through a lot of work, I don't have time to go into it in detail. We've identified that there are two main phytochemical groups of compounds, the triterpenes and the caffeoylquinic acids, which I'm going to call TTs and CQAs, which contribute to these effects. Now, ideally, you want to test all these in mice. We've done some experiments recently, which they're not published yet, but we used a much simpler model to look at the effects of these compounds. You can also do tests in Drosophila flies, which is a very common model that's used for studying human diseases, because there's a lot of genetic homology between the flies and humans. But what was interesting to us is that they show certain declines in age. So there's a phototaxis test that you can do, which measures their response to a light source. And what you find in both male and female flies is that as they get older, going from 2 days old to 60 days old, their response decreases. So they show poorer response to this light. And on the other hand, if you treat them with CAW, you can see that their response to the light really improved. So these are 28-day-old flies that received CAW treatment for 2 weeks, and then we tested their phototaxis response, and we found that CAW caused this dramatic improvement. And furthermore, we found that if you gave a combination of triterpenes, caffeoylquinic acids, or a mixture, these compounds, the pure compounds by themselves, given in groups, at a dose equivalent to their content in CAW, were able to mimic the effects of the entire extract, which showed us that these were the active compounds. However, I want to say that we did some other studies which suggest that there are, in addition, other compounds in CAW which are also active. Now, to do these kind of studies, you really need to have good chemical analytical facilities. And for this, we have collaborated with people at Oregon State University. And here, they've developed methods to do both targeted and untargeted analysis of the phytochemicals in this botanical. And what do I mean by targeted and untargeted? Well, in targeted analysis, you basically go in and you analyze very specific compounds that you're interested in, like the triterpenes here or the caffeoylquinic acids. In untargeted analysis, which is really important for these complex botanical products, what you do is you do a liquid chromatography coupled to high resolution mass spectrometry, and you basically pick up anything that the detector is able to detect. So in this case, it's able to detect up to over 5,000 different little elements within this extract. And you can then do something called principal component analysis, which allows you to compare different extracts. So these are like 8 different lots of Centella asiatica that we got from different sources. And when you do this principal component analysis, you can see that if you look at their overall composition by this PCA analysis, they actually show distinct differences, where by these samples all clustered together showing chemical similarity, whereas the other ones are somewhat spread out. So this is just a way that we can overcome this issue of complexity within these botanical extracts, that yes, we can go in and measure specific compounds, which is important if you know what the active compounds are, but we can also get this fingerprint of their overall complexity, and we can save that data as a data set for comparison with future plant materials that we get. So at this point, we decided to move into human studies, do some translational work, and we were able to use this process called interspecies scaling to decide a human dose. And you can see, and this worked out to be between 2 and 4 grams per day. Now, you heard from the previous speaker that usually for an oral preparation, you go up to 500 milligrams. So this is quite a lot. And what we decided was maybe the best way to deliver this was as a drink. And so we formulated this drink whereby you take this CAW powder, and we had to mix it with various excipients, which made it palatable and allowed us to make it more dispersible in water, and then also add some other coloring and taste agents, which would allow us to create a placebo for clinical trials. And it was very important in doing this that there were no triterpenes or caffeoalquinic acids in the excipients that we added, of course. We then had to find a good batch of Centella that we could scale up and make for our clinical trials. And when we did the targeted analysis, we found that in these different batches of Centella, there was tremendous variability, as I mentioned at the beginning, in the levels of these different compounds. And we were trying to get a plant material that matched closely the one that we had used in our preclinical studies to try and ensure that it would have an effect in our clinical studies. So what we ended up doing was mixing a couple of batches to get the right properties. And here again, these differences are illustrated in this PCA. Another problem that we faced was that many of the samples that we had of this herb actually had high levels of pesticides and heavy metals. So we also had to be careful to choose a batch that had acceptable levels of those. And we then managed to get a large batch of this from a commercial source of this plant material and make it into the product for our clinical trials. So the first thing we wanted to do was to show that these active compounds were orally bioavailable. So we took this product and we did a couple of pharmacokinetic studies in older adults, and we were able to show that indeed the triterpenes did show up in plasma in these older participants. And so that gave us some reassurance that it was bioavailable. And similarly for the CQAs and their metabolites, this was important to also look for metabolites of these compounds. We were able to detect them. So you can see the complexity of the analytical method that we needed to apply for these plasma samples. We are currently doing a phase 1 study, and this is not an efficacy study, but it's a biomarker study, as I mentioned at the beginning. Here we have older participants, and they've been randomized to receive either 4 grams of CAW or placebo for 6 weeks. And the goals of this study, of course, are to look at safety and tolerability, but also to look at biomarkers or biological signatures. And this is what I mentioned at the beginning, that before you do a very big efficacy trial, it is helpful to do a smaller trial with a smaller number of people where you just see whether the mechanisms that you saw in your preclinical model are also occurring in your human subjects. So what we're doing here is we are looking at oxidative stress, because we believe that oxidative stress should be reduced by Centella by measuring this 8-hydroxydeoxyguanosine in urine. And we're also looking at brain neuronal health, the ability to form synapses and just general mitochondrial health in the brain. using a couple of really cool brain imaging techniques. So you can do, you've all heard of MRIs for scanning the brain and other internal organs, but we can actually do magnetic resonance spectral imaging where we can detect specific compounds in the brains and their levels. And there are a couple of compounds that specifically relate to neuronal health and mitochondrial activity that we're measuring in our subjects. And then we also have a bunch of other measures that relate to neurodegeneration that we're measuring. Now, I wish I could show you the results, but this study has only recently concluded and we're still blinded and still working out the results. So going back to this roadmap, I hope I've illustrated that we've done a lot of work to really, fill in a lot of these blocks. And if we get a good result from this current study, we will then do an efficacy study as our next step. And because we had so much difficulty getting good quality centella, we've also partnered with this company called Oregon's Wild Harvest to try and grow this tropical plant in greenhouses in Central Oregon. And we've had some good success growing this and identifying a good variety to grow for our future studies. So now I'm going to move on to the second botanical, ashwagandha. And for this, we've mostly been interested in the root. This is already being grown at this company, Oregon's Wild Harvest, which is one of our partner companies. And here, there's a lot of literature on ashwagandha and its effects in preclinical models. But what has been missing is really this correlation between active compounds and biological activity. And what do we know about the chemical composition of ashwagandha? Again, very complex, very, very complex. There are a lot of different types of compounds have been reported in here. And if you're interested, I refer you to this reference that I've put here. But really, most people have been interested in one group of these because these are somewhat unique to ashwagandha. They're present in high abundance in these herbs, and they're known as withanolides. And if you look at products on the market, you'll find that many of them have been standardized to withanolide content. Again, a wide range, right? Anything from 5% to 35%. So what is correct? What is appropriate? And these are some of the things that we're hoping our studies will answer. So in our studies, we've been working with two types of extracts made from ashwagandha. We've been doing an ethanol extract, which I'm going to call WSE, and an aqueous extract, which I'm going to call WSAQ. And in this case, the first thing we did was to measure the withanolides in these two types of extracts. And what we found is, as you would expect, the ethanol extract has a higher level of the compounds of the withanolides than the aqueous extract. I say as you would expect because ethanol is less polar than water and withanolides are fairly non-polar compounds. One of the tests we did was not for cognition, but this was a test for chronic stress and depression. And believe it or not, we did this in these flies. So this was in collaboration with a group in Germany who have developed this model. So how do you stress a fruit fly? Well, what you do is you take these 10-day-old flies and you subject them to intermittent vibrational stress for a period of 3 days. So this is the way that they are stressed. And in order to test our plant extracts, we had 3 paradigms. We had one where the flies were simply given their usual food. The other paradigm was where we put the plant extract in their food just up to the time that the stress was applied. So this was prophylactically. And in the third paradigm, they received the plant extract both before and during the stress. And how can you tell how stressed they are? Well, we have this depression-like symptom test here called Stop for Sweets. Basically, you allow the flies to walk along a path and you give them the option of stopping and tasting glycerol, which, as you know, is sweet. And what you find is that if you look at the first 2 bars here, so this is like control flies. These are before the stress, they have a very high interest in the sweet, but then after they've been stressed, they lose interest in stopping for sweets. And this is a sign of anhedonia, where you lose interest in interesting things in life. On the other hand, if they were treated either prophylactically or continuously with the aqueous extract, we find that even though they're stressed, they resume this interest in stopping for sweets. On the other hand, the ethanol extract had less of an effect because it only worked when it was given continuously, not when it was given prophylactically. And this was surprising because, to remind you, the ethanol extract has higher levels of withanolides. Now I'm going to rush through the last couple of slides because I know that time is moving on. But what we found was we could improve the effect of the ethanol extract by giving a higher dose. But if we gave a mixture of withanolides that matched their content in WSE, the withanolides by themselves were not active. So that told us that it was not the withanolides that were active in this case. And so we did a big fractionation experiment where we fractionated the aqueous extract and tested to see which of the fractions were active and which were inactive. And surprisingly, the active fractions, I'm going to show you the numbers here. The active fraction was WSF 14, and the inactive fractions were 12 and 13. And when we did, again, liquid chromatography coupled to this mass spectrometry, this very untargeted method, what we found, and you can take that data and put it into this global natural product social molecular networking database, which will give you an idea of what those compounds you're detecting might be. And what we found was, surprisingly, the inactive extracts were where the withanolides and withanosides, which are the glycoside forms, were located, whereas the active extract contained tropane alkaloids. So, cut a long story short, what we concluded from these studies was that it's not just the withanolides that are active in ashwagandha, that, tropane alkaloids are also possibly important for resilience to stress and depression. And in other studies, we've basically found that ashwagandha has a bunch of different effects, but the compounds within this herb that cause these different effects seem to be different for these different effects. And that's really important to know as we move forward. So in conclusion, if we're going to do translational studies, taking phytomedicines to clinical use, I hope that I've illustrated how we can use a combination of chemical characterization and biological tests, looking both at functional effects and mechanisms in order to work towards having these standardized extracts where we know the active compounds are there, we know what the doses are, but still maintaining the complexity of these extracts to have active compounds. And so with that, let me just say that if you go to our website of the Benfra Center, you will find a lot of our publications there. Go to research and publications. You can see a lot of our publications on the work that I've described. And I want to again, once more, thank all my collaborators. These were the people involved in the Centella studies. A lot of people were involved in the translational studies, which has taken about 15 years, I have to say. And then a lot of people, again, were involved in various aspects of the ashwagandha studies, from the botanicals to the Drosophila models and phytochemical analysis. And we had funding from a large number of sources, principally the National Institute of Health and other federal sources, as well as the Alzheimer's Association. And finally, let me stop by thanking you and also thanking the organizers of this conference. And I'll be happy to take any questions. Thank you so much.
Enough for that exciting, detailed presentation. Yes, we are still on translational research. She has been able to give us reproducible research, detailed research on the use of botanicals, the drug development, the guidelines for industry, from bench to bedside. We have a question for you here. It says, in your second slide, Prof, outlining the roadmap for natural product clinical trials, I would like to know why the outcome measures focus on only biological effects alone, rather than including active compounds, as indicated in the outcome measure selection stage of the map.
Okay. Thank you. That's a great question. I think it's largely to do with the semantics or the words that are used. Usually when we refer to outcome measures in terms of clinical trials, we are referring to the functional effects. The outcome measures are usually, it does refer to the biological effects that one is observing. And so that is why that it says that. But I'd like to just point out that in that roadmap, you cannot do many of those steps unless you know what the active compounds are. So it's almost inherent. I agree that it's not called out specifically. It does seem to be based on biological effects, but the outcome measures of clinical trials are usually biological effects, and the focus on active compounds is implied, although it's not actually written there. But that's a great question. Thank you.
Thank you so much. Another round of applause for Professor Sunyana for that insightful presentation. Evidence to promote evidence-based use of herbal medicines. It's now time for, oh, there's another question there.
Yes, I'm just typing my answer.
Thank you for a great talk.
Thank you.
The question is off. Okay, no more. It's now time to present you with the award. It has been removed. The question has been removed. She has answered, yes. So we call on Professor Abimbola Showemimo, a professor of pharmacognosy, to present the award to Professor Amala.
Thank you, Professor Amala Sumyanat. I think, by the way, we go a long way a little bit because you have worked with one of our professors, Professor Dukoya. So it means that the pharmacognosy family has a good relationship with you.
And that's fantastic. Yeah.
We intend to keep that relationship going. So on behalf of the Faculty of Pharmacy and the conference, we want to present your award to you and say a big thank you to you for your time, your energy, in joining us for this conference. We actually do not take it for granted. We are very, very grateful. Thank you for giving us insights into natural production and giving us how we have to prepare for the future, because we need to be future ready. University of Lagos is a future ready university. Thank you very much, and God bless you.
Okay, thank you so much. The honor is truly mine. I'm really happy to have been able to do this today. Thank you.
Another round of applause for Professor Shoemimo.
Thank you.
Thank you all for staying with us to this point. You can agree with me that the plenary sessions were carefully selected, cutting-edge discussions on pharmaceutical research and healthcare innovations. It's now time for parallel sessions. And to give us the guideline for the parallel sessions, I call on Dr. Uloma Obani Ukoma. Kindly note that this brings us to the end of day one. You signed off from the parallel sessions. Thank you. Dr. Ukoma.
Good morning, everyone. We have 5 breakout rooms. The rooms are already open. Please choose any room of interest by clicking on the breakout room tab, and then select the button join, and then you find yourself in your breakout session. If you have any challenges with entering any of your breakout room, please let us know in the chat box. Send a message to the host or any of the co-hosts, and we'll help you get you into your breakout session. And then afterwards, feel free to leave the meeting after the breakout session, or you join any other breakout session of your choice. So if you are done with your own breakout session, please leave the meeting, or you join any other breakout session that is ongoing. So the breakout sessions are clinical pharmacy and biopharmacy, pharmaceutics and pharmaceutical technology, pharmaceutical microbiology, pharmacognosy, and clinical pharmacy. So we have 5 breakout sessions. Thank you.
It's showing on the screen. Start joining, please. The breakout rooms. Please, we look forward to your active participation in this rich and exciting academic engagements. Different poster presenters. Yes, like I said, the breakout sessions will bring this day one to an end. However, we're expecting you to join us tomorrow. The meeting will be open before 10 a.m. And I promise you, it's going to be more stimulating, more engaging, more insightful. Tomorrow is the grand finale. Don't miss it. Thank you.